Welcome to this course on deep learning and its applications and use cases in the real world. You can't turn a corner these days and not hear about deep learning. It's everywhere. And it's hard to tell the difference between the hype and the craze and the real world applications and where it's already being used today and where it's heading. And that's what this course is about. We're going to connect these concepts about deep learning, machine learning, artificial intelligence, and tie them in with real world examples from well known technology companies like an IBM or NASA to lesser known organizations that are making waves in their respective industries. We'll even look at how deep learning is encroaching in traditionally human endeavors like Jeopardy or music composition. We'll work with you to help connect these concepts to your own business and industry through a series of exercises. This course is intended for a business audience, including executives, managers, entrepreneurs, pretty much any current or aspiring leader. You do not need to have a deep technical knowledge, but a general understanding of consumer technology is useful. Things like computers, the internet, Facebook. Other courses that provide an overview of machine learning or deep learning, these are also helpful, but they're not necessary. We'll give you a nice introduction to begin with. By the end of this course, you should have a good understanding of key concepts, the basic idea behind deep learning, what it is and how it can help solve different kinds of problems. You'll also understand how it can apply to your business and industry specifically. We'll look at different business models and approaches, revenue streams, things of that nature. We're going to tie it through a series of examples in a variety of spaces. And then in the end, we'll bring it back together about how you can bring those ideas into your organization and what the future holds for deep learning. Let's go ahead and dig into deep learning. We're going to explore more about what it is and also take a step back and look at the broader area of machine learning and the emerging area of artificial intelligence. But to understand deep learning, we need to take a step back, right? We need to look at its contrast, traditional computing. If you're of a certain generation like I am, you remember a day when computers pretty much did exactly what we told them to do. It would function best with well-defined tasks. This worked really well for us, pretty much from the 1950s, even up to the last decade or so, simply because there's so much that we can quantify reasonably well enough to tell another person or definitely tell another computer how to do something. And we've been able to automate and support and do all sorts of other things, just these standard programming techniques. So it sufficed to generate enough business, enough revenue to get us really far. But obviously, it has its limitations. It can't adapt. It can't be flexible. It can't learn like we do. And that's where machine learning comes into play. Instead of getting step-by-step directions, this is simply telling a machine to go from Chicago to Los Angeles. Go figure out the best route. You go figure out, we trust you. In areas where there's ambiguity, right, or uncertainty, we don't quite know the best path, or there's too many options, it's too complex to carve everything out in advance. So we need computers to do more. We need them to learn like we do. That's in essence what machine learning is. It can be intimidating when you look out in space, how many different kinds of algorithms there are and a lot of the technology and terms. It's very mathematics heavy, so it can be pretty daunting, even just scratching below the surface of some of these techniques. But in its essence, its core, machine learning is just this. It's inputs on the left, it's doing some stuff, which we'll talk about in the middle, and then it's leading some insights, some outputs on the right. That's all it is. And on the left, these inputs, it's just information. It's things that we're used to dealing with every day in our both professional and personal life. It's information sources, so curated collections like newspapers or publications, tweets, anything we can get our hands on that's already pre-processed information. Machine learning also works on something called a training set or examples. These are basically just answers to the test, right? For some smaller collection, we know what we're looking for. So we just give it to the machine and say, find more like this. Also, machines, particularly in the robotics space, but also all of these algorithms, right? They're learning as they go. So they're taking in this information, they're predicting something. We can correct them. We can say, no, you actually thought that was in this category. No, it belongs over there. It adapts, it learns that for the next time. So that's past experience. Now, the circle in the middle, that blob that's really where most of the innovation these days comes in. It's different algorithms, different statistical approaches for looking at all this data and doing pretty much the same thing, which is coming up with some idea, some trend, some pattern that it's looking for, and applying perhaps a prediction. It's this middle block where it's really doing mostly the same thing, but the techniques that are doing that are very different. And then on the end, the insight, that's really what's driving us. It's either helping us see something we couldn't see before or doing a task of ours that we just couldn't do as much of, as quickly of, 24/7 every day of the year, like a computer can. In this machine learning space, there's so many different techniques, so many different algorithms that you can choose from. It can be overwhelming, but it doesn't have to be. Really, these are all doing largely the same things, just with a little bit different of a nuance. Some are better in some situation than others. So this gives you an idea, though, of the landscape that's out there and why it can be so intimidating to walk into this space. We're now going to dig in and talk about one particular kind of machine learning, and that is the basis of deep learning, which are these neural networks. Now, again, this is pretty much sort of the same model that I showed earlier about machine learning in general. You've got some inputs on the left, you've got something going on in the middle, and you've got an output on the right. Now, neural networks are special from the standpoint that they really handle one of their use case they do really well at is handling abstraction. So these middle layers here allow us to represent information at a higher, more abstract level that loses some of the granularity at the bottom. We'll actually go through a couple of examples of that to show you what I mean. But that's a key feature. It's that ability to abstract information, create a higher level summary, makes it powerful for something like deep learning. Now, neural networks have been around for a long time. From a theory perspective, as early as middle of last century, in the 1950s, early on, they were heralded as being the salvation, the AI finally coming to fruition, right? Everybody thought that they could be used to emulate the brain, which is why they're called neural networks, and that if you just built enough of these, just threw enough together, you would effectively approach human intelligence. Well, that was the feeling in the 1950s and the 1960s, and then the 70s and the 80s and the 90s. They kept coming back, resurging, and then they would not be able to live up to their hype and they would die down again. But the core problem really was just they didn't have enough horsepower back then to stack enough of these together to be meaningful. And that stacking is really all deep learning is. Deep learning is aggregating many, many, many neural network elements, both at the same level and then stacking them in a hierarchy so that what happens is you're able to detect a wide array of fine-grained features. And then stepping over to the right in this picture, we're increasing the level of abstraction. And the higher stacking that we can do here, the deeper we can go, the higher level, more abstract concepts we can get on the right there. And that piece, getting to this more abstract thinking, which we as humans are so good at doing, that is what has led to this explosion of interest and reality in terms of capabilities and applications for deep learning just in the past decade or so, just since about the early to mid 2000s. Let's step back for a moment and think about how we as humans learn, how we process information. If you look at the visual cortex, for instance, and then wiring that up to the brain, that's exactly how we think. So let's look at this as an example. So we've got at the visual cortex level, our eyes, when we're processing information, we're not seeing letters and numbers. We're seeing shades and borders and edges and gradients and orientation and color. We're perceiving those basically as bits coming in. But we're able to say that's a line or that's a curve. That looks like a dark stick. That's a light, round, red ball. We're able to define these things in a more abstract level again, but they're still pretty elementary, right? They're the building blocks. And as we step up, then as that information then starts to travel to our brain, we're able to say, oh, I've seen that before. That looks like an A. And those two lines next to it, they look like a plus. So we're able to do that, right? In early iterations of neural networks, we're able to do just that. They were able to do handwriting recognition. It's called OCR, optical character recognition, where you take a page, you scan it in, and it's able to actually pick up and convert that to machine readable text. Most machines stopped at that point until very recently, where the systems of today are actually able to say, an A plus. I've seen that before. That's a grade. That's an award. That's a good grade. They're able to make that connection to a broader corpus of information, sort of step beyond the literal to the figurative. And that's what's so exciting about what we're seeing with deep learning today. We already touched a little bit about how we're seeing this kind of surge in interest and capability now, largely because of computing power. But there are other aspects involved too. The first is the business need. If there wasn't a business need driving a lot of this, you wouldn't see Facebook and Google investing millions of dollars in entire server farms into doing this work, right? So, what is it about today that's different than 10, 15 years ago? It's what I'll call hyper competition. We're in an industry where we're constantly sort of clawing over the last person, the last company to try to get that little bit extra of market share or profitability. And it's a healthy, natural thing, but it does lead to this compounding where we see businesses creating returns today and generating capabilities today that were unimagined 20 or 30 or 50 years ago. It's that exponential growth that applies to so many things. It applies to business and marketplace too. We're increasingly turning to a knowledge economy. We're not producing as much physical goods anymore. Obviously, there's still lots out there, but increasingly a portion of our business is coming from knowledge and the value we can gain from that. So there's definitely competitive advantage to have systems that can glean insight out of knowledge. Now, in addition to computing power, the other scaling factor that's involved here is data. We're going to a point where everything is natively digital. We don't have things that are sourced on print first anymore. It starts digital, it's born digital. And that means that we have way, way more content than we ever could have imagined, even, again, 20 or 30 years ago. And as you've probably heard, another hype trend is around the Internet of Things, the IoT, where it's sensors on everything. There's reality and there's opportunity underneath that hype. So we've got the business team, we've got a ton of data, we've got better methods now. So they haven't changed much in the last 40 or 50 years, but there are some notable improvements, particularly something called an ensemble or a panel of experts. Main thing to know there, I mentioned neural nets or deep learning's really good in one use case or one area of thinking abstractly. But there are other algorithms that do just as well in other scenarios. So an ensemble combines all those together, and you just basically get the best of both worlds. It's an important concept from the standpoint of why we're seeing such great gains in capability lately. And we already touched on compute power. Want to touch just briefly on another tangential topic, because it's another passion of mine, and it does fit into this whole space, and that's artificial intelligence, AI. When you hear people talk, there's a lot of synonymous usage between the terms deep learning and artificial intelligence. Deep learning is a foundation that's being seen as a key piece of AI, but it's more than just that. It's really an ensemble of techniques that include sensing your environment, reacting to change, dealing with emotion, and it's approaching human intelligence. That's the idea. But the problem that's always plagued the term and plagued people that study it is, how do you define human intelligence? It is such a wide-ranging, beautiful, and wonderful thing. How do you ever quantify that enough to say that something that isn't human has the intelligence of a human? We wouldn't know, right? There's lots of games and scenarios that people try to set up to emulate this, but it's still a unsolved problem. There's this no clear definition, no finish line. So let's get back to the practical. 3 key concepts here: machine learning, deep learning, artificial intelligence. I tend to think of them in sort of this progression where machine learning is a broader category, tends to involve a lot of more traditional techniques that have worked really well and solved a lot of business problems. Deep learning is in the middle, where it's one of the best capabilities we have to handle these complex patterns and trends, and that's fueling a lot of our business growth in the past 5 years or so. And then ultimately, where trends are heading is that we'll get closer and closer to this notion of artificial intelligence. That's far enough out where you don't necessarily need to think about that from a business perspective today, but when it does reach maturity, it will open up yet another completely different frontier of business opportunity. So our sweet spot, where we're going to focus for the rest of this course, is in deep learning. You can still gain competitive advantage. You can still get that extra capability that not everybody has, right? It hasn't been commoditized like some of the earlier machine learning techniques. But it is here, it is ready to be used, and you can leverage it to tackle business problems. Now that you have a better sense of what deep learning is, let's take a look at a couple of the business models that apply to not just deep learning, but really any advanced technology, something that hasn't been commoditized yet. And there are really 4 possibilities. There's platform. This is the plumbing, the underlying infrastructure that supports all these other business models. There's service, which is really consulting, right? A custom solutions that can solve particular needs but aren't necessarily scalable. There's core, which is where you take deep learning and embody that as the core, the basis of your entire company. You're betting the farm on deep learning. And then there's enablement. And this is the broadest, the largest category where probably most of you will be, where you're looking to take a new technology like deep learning and improve what you already have, find a competitive edge, increase margin, things of that nature. So we're going to go ahead and look at each of these in turn and give some examples as well as potential revenue streams for those. Let's start with platform. And as I mentioned, this is the underlying technology, the plumbing. If you think of Microsoft and their work with Windows and DOS, they are the plumbing for computers with their operating system. The companies that are involved in deep learning today in the platform sense are providing that plumbing for the rest of the business models, the examples, the applications that we'll be talking about. I mentioned these names, IBM, Google, Microsoft. These companies have immense resources, and you really need this when you're in a platform play because the upfront capital expenditure, the R&D, the infrastructure that's needed is very extensive and can really often only be met either by very well backed VC funded companies or these larger entities that already have resources to bear. And it is high risk, high reward. You're spending a lot of money up front, but the rewards that come back in terms of revenue streams, you're able to generate license and support fees or charge an ongoing service fee. And the advantage is that if you're basically running the foundation of an entire industry or capability, everybody uses your software and there's immense capability of scale there. By contrast, there's sort of the next level up in this hierarchy of business models is a service business model. And this is consulting. This is where we're creating custom solutions using often a mix of technologies, right? It can be deep learning, but it can also be other machine learning algorithms. It can be data storage and data management technologies. So it's part of this larger mix where you're going into a company and you're providing an end-to-end solution that provides some advanced learning capabilities for whatever that might be, whether it be retail or industry or retail services, things like that. One of the biggest downsides of this kind of model is simply that it is people intensive. It's linear to scale. So if you want to grow your business, you're adding people. Consulting is a people business. And so it is difficult to get that kind of hockey stick revenue approach, but it's still profitable. And the more cutting edge you can be on the service that you deliver, the less commoditized it is, the higher profit margins you can demand. So when we look at things like license and support fees and consulting fees, they're still pretty hefty, right? It's a good business to be in. So you'll see Google, IBM Watson, other companies like this that are taking the platform technologies they've generated and also spinning off consulting businesses as a result. Next up is the core business model. As I mentioned earlier, this is really your entire offering, your entire business really has been built around this particular technology. And either you wouldn't exist or you wouldn't exist in the same form without it. So a couple of examples here. Ross is using IBM Watson to do legal research, not replacing, but augmenting a lawyer's ability to do research. Deep Instinct is in the security space, Deep Genomics, obviously in the bioinformatics space. And these are companies that are solely focused on applying deep learning into a particular industry or domain problem. And as a result, they're really betting the farm, right? There's a very narrow focus, which means it's high risk if something doesn't pan out, but there's a higher reward because they do have that laser focus. Most people, when they think about this as a business model, think predominantly in terms of product solutions sales. You're selling whatever one of these companies is building, a better security product or a better legal research aid. But there are secondary revenue opportunities. If you're able to use deep learning to solve problems that are typically done by humans, you can actually charge for that service of providing, let's say, marking up content or ad placement. You can actually charge for that as opposed to charging for the software. There's an interesting hockey stick kind of approach that works there too, because you're basically scaling up a business and generating revenue when your competitors are probably limited by the number of humans that they can throw at the problem. You have the ability to throw more hardware at it versus more people. And so there's an ability to really scale and corner the market there. So that's an interesting aspect of this business model. Now, as I mentioned, this is the one where most of us probably fall. And it's probably the most familiar as well when you think about companies that play in this space. Google, Netflix, Amazon, Facebook, these are all companies that their core business is not deep learning, but they've used it, for instance, with Facebook to make image recognition and facial recognition scarily accurate so that you can snap a picture and it automatically tags the people that are in that picture for you without you needing to go in and click and choose. It's an example of this kind of enablement business model. And so it's improving existing offerings they have. These companies, would they exist without deep learning? Yes. Would they be as successful as they are without some of these machine learning and increasingly deep learning techniques? Probably not. Think Amazon and Netflix. Their recommendation engines, which are driven by many of these algorithms, are really the hallmark of their ability to have cornered the market. Amazon's making spectacularly accurate recommendations about the books you'd like to read or the items you'd like to purchase. Netflix is recommending videos for you and generating increased revenue as a result of that. So it's definitely a key competitive advantage. And the revenue stream, again, it can be either on the top line, so you're increasing your revenue on existing products or generating tangential products that you can charge money for, or you can decrease your costs, right? You can run things more efficiently and as a result, improve your margin, your bottom line. So we've come to our first exercise. And what I'd really like to do is have you take the opportunity. When you're ready, you can hit the pause button here. Just think through with these four business models, what ones are most applicable to your industry and to your specific company. And it's also interesting to ask the question of where that appetite lies looking at the competitive landscape within your industry. Also, ask yourself what initial ideas you might have about how you would monetize deep learning in your environment. Are there particular projects or products that you think are ripe for this kind of opportunity, knowing what you know now? So, in summary, we've got these four types of business models: platform, services, core, and enablement. Different kinds of capabilities, different risk reward profile, and a couple of examples there at the bottom. More than likely, you're hovering in the core and enablement space. And so more of the examples, the applications will be targeted toward that as we explore, but we'll also touch on some of the platform and service business model efforts as well. Let's go ahead and dig into the main portion of this course, which is looking at all the different applications for deep learning in a variety of industries and use cases. We're going to touch on five main areas that have to do with how deep learning interacts with the world, whether that's looking at grouping things together or prediction, or how we interact with computers, or the other way around. Now, for each of these, we'll have a series of lessons oriented around different use cases, and we'll go through each of those for these categories here in a moment. And for each of those lessons that we'll do, for each use case, we'll touch on a number of the approaches, sort of the techniques that are applied, and then applications. And we're really going for breadth here. We want to cover as many topics, as many industries and potential applications, really a menu for you to search through and see which are most applicable to your own business, to your own industry. And a couple of notes, I would encourage you to keep an open mind here. A lot of times, the best ideas are those that you pluck from other industries. There's not a direct, obvious relationship, but applying something from one domain to another, especially if no one else has done that, can really yield to great competitive advantage. So keep an open mind on that. Also, keep an open mind on techniques that you may have tried before but failed. A lot of the use cases you'll see here have been around for quite some time, and other algorithms in the machine learning space have taken a run at them. But their accuracy or their performance has been poor enough where it really wasn't ready for prime time. It wasn't ready for the business world. Deep learning is changing that. We're seeing better quality, faster results, more fidelity that's in line with how we humans would classify things, for instance, that it's worth taking another look. So let's touch on each of these categories and what you'll be learning about. First is characterizing the world, and this is really just understanding the world around us. It's taking raw data that's coming in and processing it into something that's meaningful. And this is what we humans do really, really well. It's part of our sensory and neural function where we can take in a raw bit stream of information coming in from, say, visual into our eyes or hearing into our ears, and can process those raw signals into meaningful concepts like apple or a computer or text. We're able to process things And that's what these deep learning algorithms can do as well. So we'll look at the actual feature extraction, which can be useful as an application in and of itself. We'll also look at how deep learning can help summarize content, right? Distill out the core concepts of a particular piece of work or of an image. And then we'll also look at more of a tagging, right? Like coming up with different attributes for, again, an image, a piece of text, etc. So we'll touch on applications in each of those areas. Next, we'll look at identifying and grouping things. This is a quintessential human endeavor, right? We always are looking to group and classify and chunk things together because it makes it easier for us to then apply rules, apply heuristics. Sometimes it's done really well, sometimes it gets us into trouble. We'll talk about that with the context of clustering or segmenting, and this is really just splitting out a population or a set of objects into discrete groups without knowing up front what groups should look like. And then there's categorization or classification, where we have an idea of what groups we want. We have some data that we've already categorized, and then we use that to train the deep learning algorithms on how to classify new items that are coming in. And we'll talk a little bit about how to avoid some of that overtraining or some of the bias that can come in with these classification algorithms. Then we'll look at predicting outcomes and behavior. And this is, again, something, if you think about use cases for machine learning in general, this is a big one. This is a lot of hype surrounding it, but a lot of real world application. You're familiar with this, right? You're on Amazon, you're on Netflix, you're getting these kind of recommendations coming in saying people that viewed this also viewed this or bought this. And that kind of recommendation or prediction about both your buying habits or your behavior, and then more the prediction of the world at large and how things are evolving, we'll look at how deep learning has improved the quality of those predictions. Then we'll move on and look more at this intersection between us and computers and how we interact. So we'll look at human communication, getting to the realm of speech to text and text to speech that is starting to make automated machines that can converse with us become a reality. And it really raises some interesting ethical questions, certainly, and also just a little bit of questioning when you interact with someone on the other side of a phone or, say, a chat window for support when you're dealing with a product support issue. I've started wondering, that response really came back. It made a lot of sense. That chat window has a person's name on it, but is it really a person, or is it some kind of support chatbot behind the scenes that's been programmed so well that it's able to respond back to me in a very natural language kind of way? So we'll look at the different use cases and applications around speech, around natural language processing for text, and things like that. We'll also touch in a couple of lessons around the more abstract or fuzzy aspects of thinking and emotion, something that goes beyond the task-oriented thinking to something that's approaching what we think of as purely human, creative, original work, things of the like. We'll wrap up with a review of the other way around, how computers or robots perceive the world and how they move around in it. So we'll look at sensing the physical environment, moving around. How do you deal with obstacles and things of that nature? And then handling the inherent uncertainty. And this is a key one. If we think about all the topics that we've talked about before, it's a rather contained space, right? We're dealing with a known set of data that we're providing these algorithms. We're really constraining its world. And that removes a lot of the ambiguity that we as humans have to deal with. When you put a robot into the physical world, though, you can't just say, ignore this part of the world, ignore that car that's careening toward you at 60 miles an hour. They have to take into account everything, and they have to factor that into the decisions. And they have to do so in a way that avoids this sort of analysis paralysis that the algorithms freeze because they can't figure out what to do with enough certainty. So they have to handle that. They have to make judgment calls much the way we do. Before we dive into each of these lessons in more detail, I'd like you to start by thinking about what areas of most interest based on what you've heard so far. What do you think will be most applicable to your business and industry? This is partially so that you can focus on which lessons are of most interest to you. Welcome to our first lesson on applications of deep learning in a particular use case. First one we're going to be looking at in characterizing our world is this concept of feature extraction. This is really fundamental to all of the other topics that we're going to be talking about in this course, because these features are the building blocks for so many of the other algorithms and approaches we'll be looking at. And why is this so important? Because our world is full of features. It's how we process and organize and think about the raw information we see in the world. I talked a little bit earlier about the visual cortex and how we process this raw stream of visual information, these photons hitting our eyes, and somehow translating that into seeing discrete objects with color and texture and being able to discern where one object ends and one begins. And so, this ability of extracting features, not just visual, but auditory and text and concept, all these combine to allow us to experience the world. And machines increasingly do the same thing, and with deep learning can do so with much better fidelity than some of the earlier approaches and algorithms. So we're going to break it down and look at different types of features. And the first and one that you may be thinking about are images. We look at very granular features, we as humans and machines as well. So we might think of a feature as like a house or a roof or a mountain, but really, we're breaking it down into discrete edges and corners. We're looking at the texture or the gradient. We're looking at color and brightness. We're also looking at identifying shapes. So, can we draw these boundaries once we've gotten these edges and corners? Can we identify where an object ends and begins? And then we also characterize a bit about its size and its orientation. So we're able to do all of these different kinds of feature extraction, both with our visual cortex, and computers are doing an increasingly better job at it using deep learning. So if we're able to extract these kind of objects and such, how can we actually use that in the real world? Many ways. We're going to look at a few approaches or a few applications now, but we'll cover many more, right? We'll look at using image features to do things like classification and prediction and other aspects. But for now, let's just focus on sort of this core image feature extraction and where it happens in the real world. One of the first things that you may think about is the notion of picking objects out of a picture. In a commercial aspect, we're doing things like Google Street View, where you're able to identify particular types of buildings based on the features, the shape of that, and the texture of a particular building. It can pick out, say, the Empire State Building from Big Ben in London. It can also be used for geospatial satellite kind of imagery, and that has both commercial and obviously military implications. Some of the earliest algorithms for image extraction actually came from satellite imagery for military and security kind of work, and then also in weaponization and machine learning, where planes were able to detect that looked like a tank, that was a tank behind a bush. They were able to find airfields, things of that nature. Another common feature when we start thinking about images of people, things like facial recognition. So being able to pick out and identify what an eye looks like versus a nose versus the background, and then being able to coordinate those features to say this is a face. Another approach is looking at imagery, particularly for scantily clad or nude images, and trying to prevent some of the epidemic around the sexting proliferation that's going on in cyberbullying. And that's a great and admirable application of this technique, where it's basically using image feature extraction to figure out the flesh tones and orientation of a particular picture. Another very common use case, and this is one that has actually been probably the longest running deep learning application in the space, is handwriting recognition. This is both converting handwriting to text representation that can then be used to process or to search. And it's also used for check writing detection of signature and comparing signatures, looking for fraud. That is one of the earliest applications of deep learning in the broad commercial space. It's used heavily now in anything from Google and Google Docs and its ability to take handwritten to text. And then also looking at things like Evernote, OneNote from Microsoft, and so on. And lastly, when we're thinking about images, we are so trained by Google and others to search for things by text. We enter words and we get a list of results back. But increasingly, we're visual beings. We're snapping photos with our phones with increased rate that is mind-numbing. You can now use those same images that you're taking to run a search, whether it be taking a certain picture of a family member and you want to see all your vacation pictures with them, all the way to searching Google for related images, and even detecting whether an image has been pirated, right, has been taken. So if two images match, someone has taken that image and used it somewhere else where they shouldn't have. So this is just a scratching of the surface of image feature extraction and its applications. We'll touch on other ones in other aspects later on. Signal analysis, This is looking at the wave forms of a particular audio signature, and then looking at things like the frequency, the spectrum, and the envelope, which has to do with packaging of that information, and then raising that up to a higher level, things that we're used to when we think of pitch, like a note pitch, timbre, loudness. This allows us then to extract objects, recognize individual signatures, and isolate, say, voice from the underlying music. You might not know it, but there's quite a few applications that apply in the audio space. We think first about imagery and we think about video, but audio has a big play here. One is represented with applications like Spotify and Pandora, where they're making recommendations or selections for music based on the characteristics they're able to extract from the underlying sound. So they're not having people necessarily manually tag every song. They're using algorithms to pull those kind of features out, compare across, and recommend new music. Obviously, speech to text is a big play here. We're taking the audio, like I'm speaking right now, and having an algorithm like Siri or Google dictate that down to text that can then be used in other applications. We're also able to detect the sound, the style of a particular person, and it's almost like an auditory fingerprint. And we're able to detect a speaker based on that. And that can have commercial application, but it certainly has security and defense and military application, particularly when you think about NSA or counterterrorism targeting cell phone conversations between known terrorists and being able to identify if that person is in fact a known suspect. Lastly, on sort of the sensory side, we'll look at video features. Not much new to talk here. It's really a combination of the techniques we already talked about for image and audio, but we do weave in the notion of tracking motion and the shifting of objects in a frame. And so we're able to take the things we've already talked about and apply those in a moving space. And we're able to do things like slice episodes or segments of a YouTube video that are applicable to a search. With IBM Watson, we're able to search a concept and pull out the videos that are relevant to that using some of these deep learning techniques. We're also able to drastically reduce the space that video requires in audio by compressing them, not on some kind of algorithmic approach, but actually using deep learning to say, this is an important part of the video, this is an important part of the audio, keep this at higher fidelity and drop the fidelity of some of the background, the stuff we don't necessarily care as much about. Obviously being used heavily in robotics, in driverless cars. We'll talk about those a little bit later. So I'd like you to take just a moment, go ahead and pause this session and think through image, audio, video. What kind of applications can you envision for your business? What's already going on in the industry? What's the competitive play here? So take a moment to think through that, jot some notes down, and then come back. So we've talked about more of this external space that we see and processing raw information. Now let's talk about once we've gotten a particular kind of higher level concept like text, written text, how do we analyze that? So there's a set of features that we can extract from here, something called n-grams, which are basically combinations of phrases. Relationships between words, both in how often they co-occur and in what order or how close. The part of speech and the sentence structure, so getting a sense of the flow of the text. And then increasingly the nuance of the text, so concepts, which we'll talk about a little bit later on, and sentiment. Is this a word used in a positive, neutral, or negative manner? So there's lots of applications where text features alone come into play. Some of that has to do with, I just mentioned, sentiment and being able to tell like the sentiment or the feeling of a news story. Is it a positive or a negative news story? Plagiarism, detecting plagiarism, much to the dismay of the students of our world. Plagiarism is much harder to get away with now than it ever was before because you can use techniques to see where work has been derived. Analogous to the speech application in counterterrorism, being able to read transcripts or emails that are going back and forth and determining where there are key, hot phrases that are coming up that could lead to an attack. Those are being flagged by systems using deep learning. And we're also able to do things like tag and organize documents. So the concepts that are floating to the top out of a particular document, like a congressional record hearing, news article, tweet, etc. And finally, search. We don't think of it very often because search is this commoditized integral part of our life, but increasingly full text search is becoming not just about matching keywords, but matching intent. What was the intent of your search? What's the intent of an article and matching that up. And so increasingly, we're seeing techniques that are using these features, again, improved by better fidelity with deep learning algorithms, better recall, better relevance of search. So Google, Microsoft, others really heavily investing in this space. Think about what kind of text applications. Everybody has large corpuses of documents, websites. Think of all the content that you have or that your clients might have. How can you integrate some of these into your business? Just a couple of other emerging applications. We're not going to spend a lot of time on it, but it's worth noting. We're seeing increasingly that we're modeling not just the physical world, but some of the physical systems we see, like weather and earthquakes. And we're also seeing that applied to living systems, biological systems. So there's the same kind of techniques that we applied in more of the raw physical space. We're seeing that sort of bubbling into other models in the world. And we're also seeing it applied at a structural level. This was some of the initial work that I've done 20 or so years ago around mining features from structures like chemical compounds, DNA, RNA, proteins, and using that information to glean insight. We focus a lot on two of our senses, sight and hearing, but there's smell, taste, and touch or haptics, which as we start moving into this artificial reality, virtual or blended reality world, we're going to start seeing much more focus and effort on characterizing senses and machine learning out of those. Just to summarize, we have our four main areas that we talked about: image, audio, video, and text, and some of the applications of those down below. We had just taken a look at how we can extract features, these granular and more high level concepts that represent objects, things like text, images, video. And now we're going to look at how we can use those features to summarize content. Let's look at this example, right? Think of journalists and how they distill information down to either a headline or a small article. And this is an example from an NPR journalist that decided to go head to head with some of these machine generated content bots. He wrote a summary of a financial statement from Denny's, and a robot did. And can you tell the difference? In this example, you can, just a little bit. If you look at story number 2, that was the one that was written by the journalist. He used some more clever turns of phrase like a grand slam for Denny's. But if you look at story number 1, it actually reads really well. It looks like something that perhaps a more dry business toned audience would appreciate, and it's pretty good. In fact, most news outlets now are using these kind of programs to generate most of their bylines. If they don't use it automatically, they at least use it as a starter for journalists to then pick up and edit. So we're already seeing in this one very specific but very big business instance that you can use these machines to generate summaries that are in many ways indistinguishable from what humans can do. And that's the value. There's so much content out there right now that trying to sift through it all, whether it be text, images, video, trying to process it all yourself can be a daunting task, and it only is getting worse. So how can we use these machines to summarize the key points for us so that we can then move about our day much more quickly? So for instance, here I used a site called Summary. This is actually summarizing the abstract and some of the topics for this course. It talks about what we're covering in this course, the applications and use cases that you don't need to attend a prior course. It talks about structured attributes that are being used in different use cases and so on. And then on the right-hand side, you can see how we can summarize images and actually extract a headline for that, a black and white dog standing in a field. So let's look at two different ways that we can summarize. We're going to look at text and we're going to look at images and video. So let's start with text. There's two methods here and they are complementary. There's value in both of these. One is simply called extraction. It's identifying the snippets, the pieces of text that best represent the overall concept. We as humans like to use a lot of filler. There's a lot of stock text, a lot of adjectives, things like that. They embellish, but they don't really add to the core essence of the piece. And so what these algorithms are able to do is identify phrases and sentences that are meaningful and best summarize a piece of work. The other is more of what we as humans probably do, which is abstraction. So we're not verbatim stripping out phrases of text, we're summarizing, we're coming up with what does this piece mean, and then describing in our own words what we feel the summary is. And that's what these more sophisticated algorithms are starting to do. What's important is they both use these extracted text phrases, keywords, things like that that we learned about last lesson in generating the summaries. We already talked about media. This is a big one. This is where we're seeing a lot of successful businesses generate revenue from helping media companies and others generate summaries of content in the world. This isn't just for human consumption. If you think about it, counterterrorism, for instance, they want to listen to chatter. So they can summarize articles, social media, things like that. And then they can use that in other algorithms to detect where there are anomalies. Financial services companies use news to try to detect when it's a good time to buy a stock or a good time to invest in a certain area. So I mentioned social media and summarization as well. There's also HR. So this is a big one where you're looking at companies dealing with hundreds or thousands of resumes for any given position. How do they find the ones that are best? They have largely been bashed in the past for trying to use simple keyword screens that really miss some of the best candidates. Newer systems are able to summarize resumes in a more nuanced and robust way and really get much better quality in terms of filtering down to good candidates. We also see medical records. Increasingly, summarizing a person's medical history is important to get to the essence without all the routine checkups and all those kind of things. Well, what really matters? Using some of these techniques can help. And finally, in law and government, briefs, memorandums, things of that nature, down to, again, their essence. Now let's look briefly at image and video processing and summarization. So there's two areas where you can glean value out of either a set of images or a video, which really is a collection of images as well. One is generating a headline. So what's this summary or an outline of what's going on? You can do that by looking at similar work. So you can extract features from one set of images and then apply those to a library that's already been coded. And as a result, you can come up with a summary, right? You're looking for similar images, the descriptions of those images, and you can assemble this headline. Now, what we can also do is we can identify the most representative images. Again, thinking of text where there's a lot of filler. When we think about images and video, there's a lot of background. There's a lot of filler that really it's important for us to enjoy a movie or a news article with a lot of this filler, but we don't necessarily need it to understand the essence. These algorithms are able to generate things like thumbnails or summaries of videos, and we'll look at a couple right now. So on the application front, we've got one application that I discovered in part of the research for this is called BriefTube. It's a pretty clever app that you can add to your browser that takes a YouTube video and slices it up. They come up with headlines and chapters for different sections, and then you can basically browse through those, pick the ones that you're most interested in, get short snippets of video that represent important key points. So you're able to watch, say, a 13, 20, 30-minute video in a couple of minutes and still get the key points. So another application is geomapping. This is really big with companies like Google and Microsoft, where they're trying to map the physical world into our virtual space. So these algorithms both help them to summarize a particular view, like this is Pike Place Market, so they can tag these photos with where it is. But they can also do things like compress the size of the data they're storing, right? If you're trying to map the world, that's a huge amount of storage that you need if every image is of the same quality. So what they're able to do is pick the images that are most representative of the slices, and then they can heavily compress or get rid of certain space areas of the image and save a lot of space that way. So there's a big cost savings. We've talked about media, we've talked about news. Let's talk entertainment, sports, movies, TV. TiVo was huge 20 years ago when it came out and you could skip ahead through commercials. Well, imagine being able to watch an entire, say, football game in 20 minutes and have it pick out the key plays for you. That's what we're seeing in some of the newest evolution of technology in the entertainment industry. And then lastly, there's crime counterterrorism, loss prevention from stealing, vandalism, and then increasingly and very important is counterterrorism, identifying in video feeds where there might be an attack and being able to preempt that. Again, this is a lot of information. If you have streaming video 24/7 and try to store and sift through all that, it's not manageable both from a storage perspective and also from a human perspective to analyze all that. So these video systems are now taking key points they're identifying when something different than what it expects, and then it's presenting that as a summary of the video. So we've reached the end of this lesson, but before you go, I'd like to have you do one more exercise. First question is, what kind of text, image, audio, video content matters to your business? Is it your resumes because you are a staffing firm? Is it documents that you're producing because you're a law firm or professional services firm? Imagery that's coming in from your retail storefront? What matters to you? And then the second part of that question is, how could summarizing that help you, your customers' experience, the productivity of your workers? So go ahead, hit pause, jot down some ideas on that. So, in summary, two types of summarization: text and image and video. On the text side, media, HR, legal, medical, we're seeing a lot of use cases for summarization in those areas. And then media, geomapping, countercrime, counterterrorism on the image and video front. We just took a look at how we can summarize content using some of the extracted features and other algorithms related to text, images, video, that type of thing. And we're now going to look at a similar concept, sort of the other side of the coin of summarization, and that's tagging. If you think about papers or news articles, there's two ways that we can get more information about that we can distill something down, right? We can get a headline or an abstract. That's a summary. Or we can look at keywords or tags that are either applied by the editor or the author, or increasingly by machines. So we'll be looking at that tagging, those keywords that are generated in this session. And why is that important? Because we think in terms of labels, categories, summaries. We need to distill down all of this massive amount of information that's flooding us into something we can process. One of those ways we can do that is through tags. So let's look at this image here. This is from a software package called Clarify. It takes a look at images and uses artificial intelligence, deep learning, to tag these various images with words like nature, summer, child, things like that. It tells us what's in this picture without us having to visually look at it. So you can imagine being able to search through a catalog of thousands or even millions of images and say, I'm looking for pictures that show me a flower or show me outdoors. And it quickly whittles that down. Filtering using these tags or labels or keywords is why this topic we're talking about is so important. And we're going to look at a number of different applications and use cases for that. So let's start with looking at text tagging. Very similar approach to what we did with summarization. Again, similar concept. One way is to extract the most relevant words or phrases, and this has been done for a long time. It's really plucking out the words that are most important. With abstraction, we're going a step beyond. We're using this trained model where it can tag content even if those words or phrases did not appear. We're getting more concepts bubbling to the top, even if they weren't mentioned with specific words or phrases. And again, we're using extracted text features here. All of the applications we talked about before for summarizing content apply here: news, law, HR. But there are a couple of other applications that are relevant in other domains, more so for tagging. One of that's on the e-commerce side. Being able to take a flood of products on your website, tag them so people can use those for filters and quickly get to what they're looking for. That's a very common paradigm. We see it with Amazon, we see it with other kinds of e-commerce sites, and that can apply in a variety of settings. Similarly, shopping for events, for concerts, for meetups, things like that. The event planner or the organizer can tag those, but that's onerous, especially if you're dealing with hundreds or thousands of events a year, and multiply that by dozens or hundreds of event owners. Increasingly, we're seeing systems that can tag those events with relevant categories, topics, those kinds of things that, again, let people find what they're looking for much quicker. So this discovery and this ability to locate things more quickly, that applies on documents as well: legal documents, HR, resumes, you name it, any kind of text content where you can extract meaning out of it and then use that to drive an easier search interface, e-discovery in terms of litigation and things like that. There's one specific use case for tagging that's really important in the medical space, and those are the medical codes that doctors use when they're doing a procedure or some kind of lab result. And those same codes are then what insurers use to determine what they will cover, what they won't cover, et cetera. Increasingly, we're seeing that manual coding is giving way to automated coding. Algorithms are looking at the records, looking at the text, what the doctor had ordered, and generating those codes. Let's talk a little bit about image and video. Same concepts here that were used on the summary, just with a different output. Really, the two key areas here is looking at features that we're finding. So being able to identify those objects in a picture or in a streaming video, and then relating those. What other similar images, what other tags have been given to that? So there's a bit of a curation where you or a sample of images needs to train these algorithms so they understand what these objects represent, but still very effective. Also, YouTube search works a lot on categories. So if you're able to generate those categories on your own videos without you having to go in and tag them, especially for prolific bloggers that are doing this 2, 3 times a day, that can be very useful. Lots of applications in that space, as well as mapping, which we talked about last time, both looking at the imagery and the video, whether it's a street view or a topological satellite kind of view. Being able to tag a venue and its categories or characteristics. Is it a restaurant? Is it a shopping mall, etc.? And then with imagery, whether it's a professional photographer and organizing hundreds of pictures from a wedding or from other kind of events, or for our own personal photos. There's a picture of my family, our 2 boys, when we went skiing. And we have more pictures than I can count, and trying to create a meaningful album of those experiences is very, very time consuming. So there's certainly a play out there for providing tools for people to do that. So they're not spending so long just going through what they've recorded. This used to be difficult because everybody had their pictures locally and you had to do a desktop install, which is a very difficult thing to do from a software perspective. We're all moving our photos up to Facebook, to Google Photos, to iTunes, all these other places to store photos where we can throw a lot of hardware on a centralized problem and we don't have all those logistical nightmares of installing software. So we'll be seeing more of that kind of tagging for photos in the near future. Go ahead and take a brief moment, pause the video, and come up with some of your own ideas here. So what content in your business or in your industry are you already tagging with, say, editors or curators? What content would you like to tag, but it just wasn't feasible or practical before? Summing up, extraction, abstraction, all the different industries here. The topics we're talking about now will be building blocks for some of the other applications later on. Both with summarization and with tagging, we're creating metadata. We're describing these objects, this text, these images in new ways that are higher level abstractions or features of the very raw, unstructured content. And when we do that, it gives us a leg up. It gives us a starting point where we can then do things like categorizing content or making predictions. When we use these higher level features, we get better results with some of these more complex applications. Before we jump into clustering and classification, there's one more topic or set of topics that I wanted to talk about first. I actually went back and added this session back in because I felt that we weren't doing justice to some key concepts that you may run into in the wild, in the real world. So let's look at a few of those. The first is around language structure. We talked in some of the prior sessions around extracting features, these terms or phrases or features in an image. That alone doesn't get us to natural language processing, this notion of machines understanding what we say on a day-to-day basis. And so one of those techniques is understanding the part of speech or the sentence and paragraph structure of a document. Now, this is a lot more complicated, particularly in English. We have some goofy rules, very complex, and it's difficult to adhere to even in formal speech. Things get a lot worse with how informal we have gotten in the use of language and how pervasive that's become. It's even worse now with Twitter and other kind of social media outlets where brevity counts, and we try to cram as much information into a narrow space, and we're using abbreviations and all sorts of other tricks to try to convey intent. It makes it very difficult for a machine to understand that. There are really two approaches here, and one is not new, the notion of rule-based. That is effectively trying to encode all of our grammatical rules and shorthand and so forth into some kind of lexicon or grammar for the machine to understand. This is inherently error-prone and it is fragile. As soon as language evolves, as it does every year, these rules need to be updated and kept refreshed. Now, a newer approach is using some of the learning techniques we've talked about, and increasingly deep learning can help with this nuance of understanding parts of speech and also this notion of a structure of a document. So where does this come in handy? One area is in law or government policy, that type of thing, where we're dealing with large structured documents. So things like pleadings and memoranda that go on in court systems, agreements whether it's a merger or an employment agreement or any of the variety, real estate agreements and so forth. These all have structure to them. There are these things called clauses, and understanding what is a clause is important in its own right, where one stops and where one begins, and then being able to compare across clauses. Without actually understanding how the document is structured, you can't glean that kind of substructural information. And so this language structure detection is very important. In the media, news articles and so forth, being able to identify what are nouns versus verbs and so forth can be useful in helping to, one, actually coach journalists and others how to write more, say, an active voice versus a passive voice, and then other kinds of applications in terms of editorial cleanup. And increasingly, the notion of customer service or call center and trying to get machines to be able to answer some of the most common questions without needing to involve a human. One of the key aspects of that is being able to do this conversation in a natural language kind of way. And so these are just a handful of the applications that apply here. I'm sure you can think of some others. The next topic is something that's known by a variety of names. I most frequently hear it referred to as entity extraction. So this is taking unstructured text again and parsing out what are the people, the places, the companies, the educational institutions. Depending on your domain, you might have different needs. This is more complicated than just saying this is a term or this is a phrase, and this phrase might be important. You have to understand a variety of names that something may be called, whether it be shortened names, nicknames. Corporations are notoriously difficult, as are people's names, because we have Matthew versus Matt, or Apple Inc. versus Apple Corporation. And then you've got subsidiaries to worry about, hyphenation and other kinds of acronyms and things like that. So it's very messy. You could see the word apple, and is that referring to the company or the fruit or both? You just don't know without looking around the space and inferring intent. So here there's three approaches. One, and the most naive, is basically a dictionary, a lookup. So this is saying, if I see this word in here, that is in fact an entity. This works okay for things like stock ticker symbols that tend to be more unique, but it breaks down particularly when you're dealing with company and people names that vary. A step up from that of pattern-based, so looking at patterns of words or letters together that make a certain phrase or entity that you care about. I actually did this quite a bit when I used to work at a legal software company. We used pattern-based recognition to extract what's known as jurisdiction or governing law. A particular agreement would be litigated in or adjudicated in, or for court documents where the actual court was, getting jurisdiction, getting governing law. Learning based, again, newer approach using some of these deep learning techniques. So I already talked about one application to entity extraction, and that's in this legal context of pulling out things like parties in an agreement, jurisdiction, the court, the judge that oversaw the case, so on and so forth. HR, big help there in taking a resume and parsing and automatically populating where they previously worked, identifying the company names, normalizing those so you can get a sense of continuity across normalization across candidates. This is also really helpful in sales and marketing. If you've ever used HubSpot or something like that, it helps you organize all your leads by company and handle some of that variation in names. Obviously, media, news again. And then also in the e-commerce and entertainment area, being able to extract some structure out of there and use those as tags. One other topic I wanted to cover briefly, because it is so important as we bridge the gap from looking at these discrete documents and discrete features that we're finding to something bigger, and that's relationships. Let's take, for instance, in news again, it's not just enough to find a person's name and then find a company's name a couple of paragraphs later. You want to know if they're tied together. Does that person work at that company? Is it their CEO? Is it a chairman? Is it some other kind of role in the organization or not? And this can be people to people to company, company to company. There's all variety of combinations. And again, rule or pattern based, some of the original techniques use this, but increasingly deep learning can help tease out what these relationships are by learning from a set of data versus someone going in and hard coding all of these rules. So a lot of the same kind of applications I talked about before, not surprisingly, apply here as well. But a couple of new ones. Insurance, or sort of the financial space, when you start getting into claims and ownership, when you start thinking of particularly corporate insurance policies, understanding the interrelationship between entities is critical to apply a policy or to understand if someone has a justifiable claim. That applies across all of these professional services, financial industries. We're going to take a little bit different direction on exercise and want you to think ahead into some of the other sessions that we're going to have. Thinking about that customer service or that call center mentality or that operation, that function that you likely have in your organization. A question is, how repeatable are your company's communications either internally or externally today? How much are you already automating? Or could you at least partially automate through better handling of this text processing, right? If you're able to identify parts of speech, identify important entities, understand the relationship between them, what could you do to improve your efficiency, your operations? Take a minute, think through that, and then we'll wrap up. So, in summary, three more advanced topics that we talked about here. The first around language structures, parts of speech, identifying a sentence, a paragraph, a clause in a legal agreement. Entity extraction, these are people, place, things, usually how I think about them. And then the relationships between those entities, and also relationships, honestly, between language structure that plays well also. We've spent the last several sessions looking through some of the building blocks that we use in many different approaches. And we're going to talk about the first of those approaches of grouping things together. We're going to start entering territory that you're more likely to be familiar with because we're going to see more real world applications, things that translate into actionable insight and revenue. Why do we want to group things together? Why do we want to categorize things? Well, part of it is human nature. But of course, the real reason is it makes things much easier to act on. If you have ever built Legos, maybe with your kids, I do it all the time. It is so much easier if you spend a few minutes actually organizing some of the pieces first because you can quickly grab what you need without hunting through the pile every time. And that's effectively what we do every day in our interactions. Half the time, we don't realize we're even doing it, but we're constantly evaluating and categorizing or grouping things together. Now, there's two different types of this grouping. One is segmenting, and the other is categorizing. They're effectively the same thing, right? It's how we separate items or objects in the real world into groups. We want those groups to have similar characteristics. If it's Legos, it might be the same size, the same length, the same color. And if it's people, we might be looking for people with similar attributes in terms of spending patterns, economic factors. As we talked about in the last several sessions, we can use these extracted features, these higher order descriptions of things to help us categorize. It's much easier to do that than try to look at the granular individual attributes of every object. Now, this organization can be flat, meaning it's just a list of categories or characteristics, or it can be higher, sort of nested. We might categorize people into being thrifty or more likely to spend. And then we might drill down from there and say these are people that like to shop on the internet versus people that like to traditionally go into brick and mortar stores. Now, the main difference with these two is segmentation is what we call unsupervised, meaning we don't have any prior knowledge of what categories we're looking for. We just have a pool of data and we want to understand how it groups or clusters together. Categorization, on the other hand, says we want to put things into these buckets. We've already spent time defining what categories should be. We want to understand how new data that's coming in, new objects, how they fall into these categories we've defined. And those can either be by rules, sort of if then kind of conditionals. If we see something like this, it looks like this category. Or we can simply say, here's a bunch of data we've already categorized. Go learn on that. It's called a training set. Now, with both of these techniques, there is the notion of too much of a good thing. We have, as humans, information overload. It's very much a machine challenge as well. The notion that if you have more data, you will get better results is often a fallacy. The problem is these machines are based on statistical inferences of what is similarity, what things look like together. And if you flood it with a bunch of information, then much like us, we can come up with spurious connections or spurious categorizations that don't actually reflect reality. It's just sort of a statistical anomaly. So how do we handle that? We do something called dimensionality reduction. We're going to remove attributes. We're not going to look at the entire puzzle of everything that we might get dumped on our plate. We're going to be more selective than that. A couple different approaches. The first is human input. We can come in and say, no, ignore these variables over here. We're only going to look at, for let's say, people, size, height, weight, age, and gender. And we don't want to take some of these other categories that might have been applied in our database. Now, a note of caution here, use this one sparingly because much as before, where I said statistical inferences can be problematic, the other holds true where we have biases. We may think we know what is important in categorizing or grouping things together, but we may be wrong. We often go with our intuition, and that intuition isn't necessarily backed with statistical rigor. So use it as a last resort or use it in concert with some of these other options. In data, a lot of times you have the same handful of features that are reflected over and over again. It might just be a variation on a theme. You might be looking at a percentage of a number versus an absolute. And what happens is you end up with all of these different kinds of categories or variables that all mean the same thing effectively. And there are techniques for removing those. We can also remove those that really don't change. So if this attribute is the same on every single object we're looking at, if we're looking at a pool of men and we choose gender as one of our characteristics, that's not going to be very useful. We want to take those out that never change. Again, techniques exist for that. Finally, there's two other approaches that are more statistical in nature. One is we can look for what are determine important features. If we remove what's non-discriminating, we can look at what are discriminating. So what factors, and this is a technique called principal component analysis, that let us select the variables that have the most meaningful impact in separating our objects out. And there's also a technique that's called experimental design. So this doesn't apply to a single analysis, but you actually do a group of analyses and you either keep adding variables in or you remove them. So you start big and remove, or you start small and add, and you'd see whether your results improve or not. And then there's one last technique that comes from the research or scientific background called the design of experiments, where you actually create a host of variable settings that are intended to cover a reasonable percentage of options, and then you see which one performs best. So in summary, segmentation is also called clustering. That's when we don't have our categories. We don't know them in advance. Useful, obviously, when we don't want to spend a lot of time training algorithms by giving it pre-classified data. Categorization or classification, that's when we know those categories in advance. Lastly, dimensionality reduction. We want to take out the features that are not as helpful and keep those that are most discriminating and useful. And there's a number of techniques that can be used. Biggest word of caution here, beware of your biases. Beware of what we think is important. It's often not the case in reality. In this lesson, we'll be taking a look at segmenting. It's also called clustering. This is effectively grouping items together, and they can be any items. They could be people, places, organizations, transactions, products, you name it. Grouping them together, but not really knowing upfront what kind of groups or categories we're expecting. So we're using it more to segment a market or a set of objects as opposed to categorizing or labeling them up front. Now, there's a general approach that applies to all types of clustering, and we're going to cover something called data clustering, so looking at databases of information, text, and images. But these steps that we'll talk about here apply really to any of those. We need to understand what a similarity measure is between two objects. So if we have two people, how similar are they? And there's a variety of techniques and measurements for that. But the key piece in all of this, we're going to be using features. Some of those same features we extracted from objects and items in the prior lessons, we'll be using those techniques here as well. So we take these features, these items, we compare them together, and we get a similarity measure. All of these different algorithms basically take multiple passes or approaches of organizing the objects and then assess how similar the groups they form are, how much items within a group are similar versus dissimilar to all of the other groups, all of the other items. And the idea is finding those, again, that are optimal. If we don't have categories up front, how do we actually know the clusters we're finding are good? So there are a variety of metrics, statistical measures, such as the silhouette coefficient, that help you understand, generally speaking, is this set of clusters better than the last time I ran? So it's sort of an optimization problem. How do I get better and better? Clustering's been around for a long time. It's one of the original data mining techniques. What's new is deep learning, and it helps us around this periphery or the scaffolding of clustering. So we talked a little bit about dimensionality reduction last time, and how do we choose the variables we want to use in clustering to get better clusters. Deep learning helps with that because it can evaluate and learn how changes in those variables work And it can do that in an automated fashion, almost as much as a human experimenter would do. Beyond that, all of these algorithms have a variety of parameters that you need to tune, whether it's the number of clusters or something called a density measure. And it can, again, use this automated approach to evaluate a ton of different options and do that very quickly and then settle on one that is best for the approach. And then lastly, something called an ensemble or a panel of experts, where we don't have to just choose one algorithm. Recent advancements allow you to run all of these algorithms, often multiple passes and with different parameters, and then pick which of the algorithms themselves and the set of parameters and the variables. It sort of lets you choose all those together. So it's a really nice approach to iterative development that's really improved the quality of clustering in the past several years. Now, as I mentioned, there's three types. The first is data clustering, and this is probably what you're most familiar with. It's probably the most applicable to your business today because you have treasure troves of data warehouses and other kinds of transactional information, financial, et cetera, waiting to be clustered. Some pre-processing is usually required, so we need to handle categorical values, and there's something called category expansion that pre-processes it for these algorithms. And then we also need to normalize our numeric values. Things like annual salary translate to number of kids, where the large salary number doesn't outweigh the smaller child count number, for instance. And we also have some custom similarity. If we have complex cases like chemical structures or genomic data, DNA, then we'll have a different kind of similarity measure that can handle some of the variation and fuzziness and matching of some of these items, but still get good quality results. We've talked more about categories or industries of applications. I'm actually going to talk about discrete examples now. This is a URL down there if you would like to visit it, where a insurance company used some of these same kind of machine learning techniques. They took in survey data they've gathered from some of their customers, demographic data, not personal geographic data, but more this area, this sort of zip code, and getting a sense around that. And then also looking at credit information in the aggregate. And they pumped this all through some clustering algorithms. And what they found were 5 clusters that came out. Now, it didn't come out with these names. It just came out with here's 5 groups of people that tend to have similar buying patterns. The consultants went back and actually labeled those categories. And what they found were there were sort of the internet, the new age buyers, people that are buying on the internet, people that are more traditionalists buying through mail and phone. You have people that were worried about budget, people that probably weren't as worried about budget. And those were people that were either loyal to an agent or just get it done. So this is an example of market segmentation that's really huge in the industry if you think about e-commerce and brick and mortar retail, grocery stores, things like that. This is a project that I did about a year ago where we worked with a global health foundation to understand better how malnutrition and stunting occur within Saharan Africa and Asian countries. You take a technique in one country and you go to apply it to another country. The social mores and the social demographic and the geographic differences are so profound that it doesn't work. But if you're able to take some of these clustering techniques and find out which countries looked similar based on a bunch of data, we had over 500 metrics, then the idea is a country in the same cluster is more likely to receive aid or benefits in the same way, and it would be a better application of need alleviation than if you just did a blanket approach. This is almost the personalized medicine approach for health. Any kind of scientific data, whether you're looking at weather, seismic data for earthquakes, geological data, all of these apply pretty much to any data that's numeric or categorical in nature. Certainly finance, trying to categorize or segment stocks together so you can create, say, mortgage portfolios or hedge fund portfolios or stock portfolios. And then obviously healthcare, both on the genomic side, so sort of the personalized, very detailed medicine, up to more of the healthcare outcome, hospital, and improved care there. So let's move on and touch a little bit on text clustering. This takes some of the feature extraction techniques we talked about before, particularly things like entity extraction, keywords, concepts. We can also use the metadata or context around it too, so the author, the name of the document, when it was created. And the idea is then calculating similarity between those documents. And what we end up is with a corpus that's segmented out. So we can see this group of documents or pile of documents over here tend to have the same characteristics. This collection over here has a different set of characteristics. This is another application that I did within the last year that is in the digital humanities space. This is taking often very old texts, digitizing them, and then using some of these same kind of machine learning techniques to find new areas of research. And in this instance, we worked with a professor that was studying something called hermeneutics, which is the historical implications and context surrounding religious texts. He used this tool that we built for him to cluster the documents and the terms and phrases that were found in it. And he used that to look at the boundaries between clusters and actually discovered a new research area in the cluster boundaries, sort of where these terms collided, that has actually never been treated in research circles before. And so he had a brand new area of research that he never would have gotten either reading individual texts or just being on the ground in these places. It was really through this tool that he came to this new discovery. There's lots of applications, obviously, that are more commercial in nature. Thinking about email or personal productivity, how helpful it would be if you could log into your Gmail, log into Evernote, and all of a sudden find that your emails or your notes have automatically been categorized and grouped for you. So you know which emails are personal versus which ones are business oriented, which ones you need to respond to, and which ones you don't. So imagine the power of something like that. And there are certainly companies working on that. Same on the social media space, whether it's Twitter or some of these other platforms. And then certainly more on the defense side, anything that is text-based, which can include texts, emails, transcriptions, things of that nature. And you've certainly heard the news reports about the NSA and other agencies using techniques like this. And then lastly, in the legal space, there's something specifically called e-discovery, where companies, when they litigate with each other, they have millions and millions of documents that lawyers used to go through by hand. And increasingly, they're using computers to help sift through the information. First using search techniques, but more recently using clustering techniques to try to group content together. So you can take one representative email, for instance, and review that, and then know that it's similar to 100,000 emails like it. And last, we're going to talk briefly about image clustering. This is very similar to the other two topics, but here we're obviously looking at images, and we're using some of those low-level images, features that we've extracted, as well as tags and other metadata. Key point to note here, and why you've probably seen image detection being much more prominently associated with deep learning, is that the other two techniques we talked about, there were reasonable approximations and approaches that existed before deep learning. With image processing, it's always been much harder. It's just more sensitive to noise. It's more a difficult problem, and therefore it's more conducive to some pretty dramatic leaps through deep learning. And so we'll see things like grouping your personal photo gallery together, particularly as those move to the cloud through Flickr and Google and other services. Certainly Facebook with its image grouping and facial recognition and that sort of suite of tools. And then certainly defense and military applications as you're looking at, say, satellite photos. Also just in the geospatial sense in general as we become a Google Mapsified world. Think about this within your context. One key question that comes to mind immediately is, how do you currently segment your customers? This is something pretty much every company in the world goes through. How do you currently segment them? How do you target promotions or products? And would you benefit from better segmentation? Do you think you're doing well as it is now, or can it be improved? Also, what other data or content types could be segmented? Not just customers, but there's other things, products, transactions, financial data. Think through some of those options. And then lastly, if you've already attempted one of these projects and they've failed, spend a moment to reflect on that and why you think that's the case. 3 types of clustering: data, text, and image. They all operate on the same approach of using these similarity metrics to figure out which items belong closer together and in these groups versus others. And they're just using different types of data. The markets that they apply to, the industries, just depends on what type of data those industries most often have. We just covered clustering or segmentation, and we're going to look at the other side of the coin, which is categorizing or classification. These are really 2 very similar techniques. The main difference being in that in segmenting or clustering, we didn't know up front what categories or groups we wanted. We wanted to let the algorithm decide just to sort of naturally segment a population. We want to apply our own real world experience, our categories. We've already set up a taxonomy, let's say, and we want the algorithm to help us categorize a bunch of data. We might be able to categorize hundreds of items in a given time, but let's say we want to classify thousands or millions. Algorithms can help us with that. Key piece here is what we call a training set. This is where we're providing data that's already been pre-tagged or pre-labeled. This can be something we've done personally or something within our organization. It can be done by our customers, our users. Think something like Facebook, where people are constantly tagging posts. Or it can be even what's called crowdsourced. You can put it out to the broader community. There are things like Amazon's Mechanical Turk, which you can basically pay and have people go in and do relatively straightforward tasks, and you can accomplish these things rather quickly. So, lots of different ways to get that training data, but the idea is you need a reasonable sample. And you need enough that the algorithm can discern real patterns. So you need more than, say, one example of each category, but you don't need to necessarily get carried away. A lot of the newer techniques can work with less training data than what you used to need 5, 10 years ago. So once we've had this training set, what we're going to do is identify the features that best predict our categories. And it's usually a combination of features, and you can think of it almost like a rule or an if-then kind of conditional, where it's actually one of the types of approaches is something called a decision tree that does exactly that. If weight is less than 200 and the person is a non-smoker, then they have fit in this category, say for insurance policies. Now, the algorithms learn on a subset of the training data. We don't use it all initially. What we do is we leave some of that out. We train the algorithm, and then we use the piece that's left over as a test of validation. There's lots of different techniques. There's something called cross-validation that does sort of slicing of the data and does many permutations. There's all different kinds of statistical techniques that are out there. As with clustering, classification's been around for many years, and we're reasonably successful, particularly with certain types of data where the categories were very clear and the rules were very clear. Deep learning helps us, though, with improved algorithms. This is the sweet spot of these deep neural networks we talked about in our introduction to deep learning. They are able to pick up more of the nuance. They're able to abstract patterns, look at higher order patterns that can help be better predictive in finding these categories. Additionally, as with clustering, it's able to help us with some of the feature selection, picking out which features we want to include in our model, tuning that, as well as figuring out what our training subset should look like, and then also helping to tune the various parameters that many of these algorithms use. Three types again: data, text, and images. We're going to spend less time talking on data and just a little bit of time on text because it's largely the same. The key difference here, we know our categories. It is helpful. It's a different set of data, but really the applications are the same. So we're using a structured database, we're doing pre-processing. We have different algorithms and metrics for genomic data, for chemical structures, and so forth. The application's also the same. Scientific data, healthcare, genomics, personalized medicine, finance, very common for these applications. Text classification, very much the same. We're looking at extracted keywords, concepts, the metadata. An application that actually I worked on extensively about a decade or so ago. So these were before a lot of the deep learning techniques came out, but we were using some of their predecessors for this work. This was working at a large legal content provider, and we would go into law firms and other entities with legal kind of content. And they would have these document management systems or repositories that had millions of documents. One firm I remember working with had close to 50 to 100 million documents in this repository. They're lawyers. This is pretty much what they do day in and day out, is they create content. Now, the challenge is finding that content. You can use full text search, but that only takes you so far. If you're doing things like applying records retention policies, or you need to secure confidential material, some use cases also just finding the material better, whether it was more of an agreement on the corporate side or more of a brief on the litigation side. It could be very confusing to get those two muddled up. So we took a technology of classification, we built rules and used algorithms to build those rules for us that were able to take a bunch of content and distill them down into the different types of legal documents that are available. That was very useful for a variety of reasons. It was one of our more popular services because of this need, right? It's a universal need to organize our world. As I mentioned, a lot of the techniques here, very similar and very applicable, whether you're doing freeform clustering where you don't know the categories or whether you're classifying into groups. Image classification, if I had asked you beforehand what was the first thing that comes to mind when you think of deep learning, this probably was in the forefront because we see it a lot with Facebook, with Google, Microsoft as well in the mix. The approach here is the same. We're going to use a lot of our extracted features and tags. Now, though, since we have categories in mind, and this is particularly true with images, we're constantly categorizing our images, whether it's friends on Facebook or whether it's personal photos from vacation. We have a taxonomy in mind. We have these labels in mind. And there are systems now that help us with that. One is a product called Cafe that comes out of Berkeley. This is Cafe classifying a picture of Thomas the Train as an electric locomotive. Pretty accurate, even with the face of Thomas on front. So systems like that can classify and tag photos. Clarify is another one that handles well things like backdrops, backgrounds, and such. Now, once we're able to tag these items, there's a lot of different ways you can go. So one of those I already mentioned, which is Facebook, one of the leaders in this space. Because of this, this is a photo of a bunch of people on a beach. They're jumping around, they're goofing off. Facebook now is able to actually detect and tag many of these faces, despite the fact that they're obscured. It's low light. You've got one person with his head turned to the side, several people with their arms up front, or another person's arm in front of them. And where deep learning has helped is that it's able to handle a lot of this noise and variation. Whereas we people, we can tell that's Johnny right there. We can tell that because we're able to piece together these sort of missing elements and infer. And increasingly, these stacked neural networks are able to do the same. So it's not just the fact that they can tag a pristine image, but they're able to handle a lot of this real life scenario that makes it so powerful. Now, another application for that is around cybercrime, particularly related to nudity and sexual content, sexting, particularly with minors. It's a big epidemic right now, and it's becoming more and more pervasive with smartphones in the hands of a lot of our youth. What we're finding in their applications are helping to combat that. So the FBI and other forensic companies for a long time have been using software to scan hard drives, particularly for child crime and searching on people's computers. That's also translating now to the smartphone world with the ability of both cloud-based deep learning and the ability to do it much more quickly and effectively. I have to find an appropriate nudity image to show here to convey that. And this was a clever site of, is it nude? And it's a hairless cat. So I thought that worked well. What other data do you have at your disposal valuable for you to classify, right? Jot some down. Customers, buying patterns or transactions, images that you might have, security footage, HR data. Just sort of think through all the different kinds of data that you have at your disposal and perhaps rank them or star a couple of the ones that are of most interest. They'll give you some ideas of what you might tackle in the near future. Wrapping up, data, text, imaging, same as with clustering. These are sort of an order of complexity. So it's relatively easy, more or less, to do clustering or classification on structured data. Text, it's a little bit harder. We have to do some pre-processing and extraction. Images have traditionally been the hardest and therefore benefit the most from deep learning. We're going to delve into an area that I'm sure you have heard a lot about or seen a lot about. This is not new to anyone. It's making recommendations. And this is really a close cousin to the clustering and classification approaches we looked at previously because it uses a lot of the same foundational techniques, similarity, features that are extracted, and we're really just applying it to a different target or a different end game. Now, when I say that you have likely come across this, it's because you can't trip over a website these days without coming across it. Obviously, Amazon up in the top left, or some of these other kind of e-commerce sites where it recommends other items that you may want to purchase because either somebody else bought something similar or they pair together, or a variety of other machinations of how you might think of recommendation. That also applies to the Kindle and ebooks, and obviously Netflix too, recommending other movies or shows. And you can see here by some of the titles that our tastes and our family vary widely. My wife has some shows that she likes. I am into the science and documentaries. And then, of course, our kids watch it too. We'll talk actually a little bit about how deep learning can help tease out some of these personas or different users in a system like this. This is not an area that I'm very familiar with, having been out of the dating scene for 20 years now, but apparently there are sites like Tinder and all these other kinds of dating sites that you can swipe left, swipe right. Their entire business model is built around this notion of a powerful recommendation engine, right? A pairing of people. And this is the original matchmaker in machine form. So those are the obvious ones that you likely have heard of. Now let's go ahead and talk about some of the less obvious ones. Now, this one is in the machine learning space is one of the best known examples. And this is good old fashioned brick and mortar retailers, and particularly grocery stores. Kroger was one of the trailblazers in my backyard in Cincinnati, Ohio. One of the trailblazers in this notion of using recommendation engines or systems to guide product placement. Unlike e-commerce, it's not putting an item right in front of your face, but it's using it to drive decisions. So this is a decision support tool for all the different people in the retail space that are designing the layouts of the stores and where to put items. Now there's this now legendary story about a algorithm that was able to detect that newborn dads would buy milk, diapers, and beer. So the idea was to put all those together. Now, that story actually, as far as we know, isn't really true, but it paints the picture. So it's this idea of recommending items that go together. Grocery stores used to then put all those items together sort of in the front of the store to make it convenient for you. Then they discovered that wasn't a great business model because you got in and you got out and you didn't buy anything else. There were no impulse buys. So now what do? They put beer in one side of the store, milk and eggs in the completely opposite side of the store, and they put them in the back and they make you walk through the entire store. So they're actually using it as almost an anti recommendation. Say, people buy these together, so spread them as far out as you can. A lot of the things that we think of when we're thinking about these machine learning techniques are in the electronic space, but it doesn't have to be. It can very much apply to the real world, to the tangible things we touch every day. As I mentioned, we're calculating similarity between these objects, these items, and we're using often the features that we extracted and we talked about earlier. Now, the key difference here is we're not looking to classify, we're not looking to group items together per se. What we're really interested in is this target. There's an object of interest, and it might be a movie that we've selected, so we want to see related titles. It could be my entire shopping history, it could be me. They could be using personal data about my account and my background and history to make recommendations. I used to do recommendation engine work within a company, and they were often initially disappointed with some of the results that came from some very early proofs of concept because we weren't looking at the entire massive data, or maybe it just wasn't there. Search engines in the corporation may get a couple of hundred searches a day. Google's working with millions and millions of searches every day. So they have a bigger pool of data to work with. Now, deep learning can help with this. It improves the quality and the nuance, and it can help tease out multiple users. It can understand a level of granularity that some of the traditional or the older techniques and recommendation engines really just couldn't. Now, one key point here, and it's more of a cultural fit and acceptance than it has anything to do with either the approach or the applications, and that is people tend to accept recommendations that come from people they know. The highest level of acceptance is recommendations from their own friends and family. Then there's recommendations from other people like them. And then there's recommendations from complete strangers. At the very bottom of the pile, recommendations from machines. If you come out guns blazing and saying, my big computer recommends that you go do this, your adoption is going to be terrible. And the reason I mention is so much of, if we look back at some of these sites, so much of them couch it as though a friend is telling you this, or at least it's some person that's like you. It never comes out and says, this is a machine doing this. So it's something to think about when you introduce these kind of capabilities. And we're going to talk more about adoption and buy-in a little bit later in the course, but I wanted to bring that up now because it's so critical for recommendations. It will also apply to predictions, which we'll be talking about next. A few more applications and some links here for some case studies that talk about recommendation engines being applied in a couple different industries. And here, banking and insurance. Tried and true, hundreds, maybe thousands-year-old business model, right? But increasingly in this hyper competitive space, they're having to differentiate themselves and produce ever higher profits. These sites are beginning to use these same kind of recommendation engines from e-commerce and apply them in recommending new products, recommending what insurance fits best for you, things like that. Last, but definitely not least, is the notion of search and retrieval or information retrieval. I want to query a system and get information back and have it be immediately useful. And Google, obviously the pioneer, but certainly not the only one in the game. And I just took a screen grab from Google search, and you can see just on the front page, there are actually 4 different recommendations going on. One is recommending, as I type, searches that may be applicable, right? Narrowing my search. So deep learning applications in healthcare versus in finance. It also suggests not just content, but actually sources. Because I'm searching for something that's a little bit more technical, it says, here are some scholarly articles for you that I might be interested in. It assumes I might be a researcher or a student or a professor. It also does something called result spotlighting that not only moves something to the top, but brings additional context. It really makes it stand out. And that's another type of recommendation. And then as you scroll down, there's this notion of related searches. It doesn't say, here's some related searches for you. It says, people also ask. Very specific, very personal. And that doesn't just apply to text. I spend a lot of time searching for loads of transportation and animals because my 5-year-old is obsessed with those types of things and wants me to constantly print them out. So I spend a lot of time in Google Images doing searches. And for instance, this is one I did for him the other day for Disney Monorail. And you can see here it comes up with recommended tags or filters, right? Does it mean Walt Disney World's monorail? Perhaps the one that goes through the Contemporary Resort or different park. And then it also recommends related images. And these aren't just from the same site. They aren't necessarily carbon copies, but it's picking out those features and finding other related pictures where you can see here there's a water feature, there's the monorail, there's the sky. So you're getting a lot of that repetition, even though the picture orientation is very different. So we covered a lot, and I just want you to take a step back. This is such a critical area. Ask yourself what products or services within your organization would benefit from this notion of systematic recommendations. You probably are already doing a fair amount of at least analyst-driven recommendations. So you have people analyzing the data and then saying you should be pitching this kind of deal or this kind of product when someone comes in that's looking for another product. What more could you do if you could make it into an engine that would always do that? So take a moment and we'll come back to wrap up. So, in summary, we've got the approach, which is looking at these structural similarities between our target object, the thing that we're interested in, and everything else out in the universe, the other items. So, we're trying to find those things as group closest to us. And to do that, we need a fair amount of data. We can't do this if we don't have a history to work with. And deep learning does help us. It's improving the nuance and the quality of our recommendations. It is a large part of why we're seeing much better recommendations than we were in the infancy of a lot of these products. And lastly, on the applications front, we touched on e-commerce and media, books, movies. We talked about online dating, and that doesn't just limit to the social dating aspect. This is really any people matching. So we think of LinkedIn, we think of HR. Those are other applications. We talked about brick and mortar retailers, finance and insurance, and then lastly, search and retrieval, which is really critical for a variety of research and general productivity needs. A lot of the techniques that we've covered, a lot of the applications have been relatively safe. We aren't going out and making bold assertions. We're not really interacting with the world. We're mainly providing suggestions, decision support tools. Starting with this session, we're going to start making predictions. The predictive analytics, in many ways, are very similar to classification or recommendations, which we just covered. Same techniques, just a slightly different outcome. We're leaving this space where we have some degree of wiggle room, and we're putting forth recommendations that could be life or death. Where deep learning really comes in and why you're seeing this explosion of predictive analytics applications and products is because we're able to have this more nuanced understanding using these deep neural nets. And then there's a variety of other techniques that deep learning helps with also in terms of selecting the variables or the features that we're interested in, tuning our algorithms, and then assembling the results into this sort of panel of experts, picking the best results from a number of either algorithms or trained systems. We're going to go through a variety of applications. So most of this session really will be just looking at the applications because it's such a rich space. That's where we should be spending our time. So let's dive in. Now, the first is one you may have heard of. This was a competition back when data science competitions were all the rage. They've sort of died down a little bit in the last few years, but still out there. Kaggle was one of the original companies and the leaders in this, and they partnered with Heritage Provider Network, which is a big insurance provider in California. They were looking to improve outcomes for their patients and really to try to prevent hospital readmissions. And so they put forth this competition. A lot of different data science groups competed. A lot of the techniques we were talking about in terms of deep learning, classification, prediction, they were using this. So the idea is that the competition provided anonymized health records, both hospital records, doctor visits, prescriptions, labs, things like that, for 3 years for a group of patients. And then the goal was to try to predict in the fourth year whether they were in fact hospitalized or not based on that historical data. It sounds straightforward, very, very tricky. Humans aren't great at predicting this. So to ask a machine to do that is pretty difficult as well. Somebody actually did at least get the consolation prize for that competition, so it's possible. Moving into more recent times, there are two very different applications of some of the same techniques. A variety of companies are doing this. One is predpol.com, where I got this screenshot here, that is looking to predict crime based on time of day, location, past events, things of that nature, and trying to predict really where crime is most likely to happen, not so much to go and try to prevent it, but to increase police presence, build the network in the community, try to improve the situation there so they can target their forces more effectively. And this is being deployed around the United States. On a very different scale, IBM Watson is using its techniques in healthcare, and particularly around personalized medicine. So they've started using Watson in a variety of cancer institutes and hospitals to try to better understand an individual patient's background, their genetics, and review lots and lots of literature on the best treatment options for a particular type of cancer for a type of person. So it's a much more individualized approach in trying to predict really a series of potential outcomes that doctors are working with. Now, an interesting bit about that is that the doctors were initially very reluctant to work with Watson. They didn't believe that their knowledge could be codified in a system, and they weren't accepting the recommendations. So they actually made Watson a bit more humble. It became more of a partner, almost consulting with Watson as opposed to dictating an answer. We'll talk a lot more about that kind of approach when we cover adoption of AI projects and deep learning projects in a subsequent lesson. Now, the predictions don't need to be quite that earth shattering. Uber and some of its competitors, as well as other adjacent spaces, are using predictive analytics to try to determine where things should be, where people may be going, where they can bear rates higher, where traffic's going to be, all these kind of things to help improve their service. And you see that with companies like Walmart and Amazon, both brick and mortar and e-commerce, where they're using predictive analytics to improve both supply chain, so positioning raw materials or packages or what have you in the right places at the right time to anticipate demand. And you're also seeing it even to anticipate items that an individual may buy when items are most likely to be returned. So also theft as well. So when items might be most likely to be stolen, so that they can have those annoying tags put on them and that I always seem to forget to remove. Now, bringing it a little closer to home, there's a number of applications that I've personally been involved in. Want to touch on those as well. One of them is an older example, but actually touches on some of the work that now Watson is doing in healthcare. The first was a company that I worked with developed a series of predictive tools to help pharmaceutical companies and their researchers identify which potential compounds would be both the least toxic and the most effective to treat a variety of some of the most important medical challenges of the day. So cancer, HIV and AIDS, and a variety of other maladies like that. They were looking at millions of compounds and trying to predict which ones would be the most effective. More recently, had the opportunity to work in the financial services sector. Not surprisingly, a lot of interest in predicting change in stock market, in commodities and futures trading. So all of these complex financial instruments, being able to predict even better than a flip of a coin, as long as it tends to be biased on the upside, you can perform very well. And so you've got a lot of companies, even though you may not hear about them in the news, but it's out there. And they're doing a lot of work to try to improve the way they can predict and then buy and sell these commodities. And we talked a little bit about transportation and supply chain management. And another use case for that is predicting failure. So I worked with a company that's building sensors for trucks to try to predict tire failure, brake failure, things like that. It seems rather mundane, but it actually, for these large trucking companies, can cost them millions of dollars a year in lost productivity, damage to the truck that can cause accidents. And so they're looking to better predict when something will fail and then replace it before that happens. Obviously, airlines very interested in that technology as well. So we've gone through a litany of examples. Wanted to now bring it back to your home and talk about two sides. First, customer facing. So, what customer facing predictions could you use that might either improve your top line or your bottom line? Either improve the cost of doing that service or improving overall revenue, bringing in new customers. And then also think about internal operations, your supply chain, HR, finance, any other specific business function that you have. How can you use predictions there to, again, improve profit, reduce your costs? There might be some revenue opportunities there as well. So take a moment, think through those, jot them down. This is where you will start getting more traction because these examples are much more near and dear to people. They understand them, they can see the outcome, see the implication than some of the earlier techniques we'll review here in a moment. Summing up, so we didn't spend a lot of time talking approach here because the approach pretty much the same. Really big difference is the target, the outcome that we're looking for. And in this case, one or a few future facing outcomes, again, higher stakes. And then deep learning really helps this in a variety of ways. We can build the models, we can tune it better, we can select those features, we can combine models together. And then applications, sky's the limit here. We talked about healthcare and medical, personalized medicine, talked about crime prevention and prediction, and then obviously a variety of use cases in sort of the transportation, supply chain, and e-commerce space and financial markets. That's just a small list of the large variety of applications here. We're switching gears a bit and looking now at how we interact with computers and how computers interact with us. This is moving beyond the safe zone that we've been, where we've largely been looking at constrained environments, constrained data sets. Even though the data may be a bit messy, it's a known space, it's a closed space. And that makes so much of the work that we do in machine learning and in deep learning that much easier. We're getting out of that space now. We're getting out of our comfort zone and we're talking about the messy world of human communication. And how hard can it be? It's insanely hard. This is one of the most difficult challenges in computer science, and for good reason. We humans have adapted to communicate with each other, which means we develop all kinds of shorthands and idiosyncrasies and cultural references that are very difficult for traditional programming to handle. Now, the good news is that deep learning gives us that nuanced complexity and that abstract thinking and pattern recognition that is critical to understand we humans and how we communicate. And it's not just written or spoken word, it's our nonverbal cues too, and we'll talk through that in a moment. I want you to be patient, perhaps a bit forgiving of the past. If you're like me, you've had an incredibly frustrating phone call, probably several, with an annoying auto prompting computer on the other end trying to get through to a human, right? We've all heard the stories. My personal favorite was I was stuck on a plane that I knew I was going to miss my connection. I was trying to get through to Delta. This was probably about 15 years ago. So again, the technology was not great. And I remember yelling into the phone trying to get the correct set of prompts just to get to a person. And it kept rerouting me and rerouting me. So again, please forget the past. The technology has evolved considerably since then. So we're going to look at three items. We're going to look at text, speech, and nonverbal. And let's start with text first. This is recognition of either printed word or handwritten word. And this is really the classic use case for some of the earlier neural networks in things like check handwriting and verifying signatures and also fraud detection. So it's largely solved for either clean typewritten text. So if you do what's called OCR, optical character recognition, of a page from something that was printed, say, in the last 20 years, it's pretty good, pretty faithful reproduction because it's a pretty standard print. Now, where deep learning comes in is when we start looking at either lower quality typewritten text. So think about something that may have been produced hundreds of years ago, and certainly handwritten text. The difficulty is why so many of the traditional techniques failed and got a bad rap for this recognition. They capture these strokes, the angles, the positioning of the letters or of the individual parts of the letter as these low-level features. And then they predict what the most likely letter is based on the combination of those features. So if it has two slanted lines with a bar in the middle, it's a capital A, most likely. So that's the kind of thing that it needs to handle, especially in handwritten text. What's key is that either training on the individual person that is using the system or a whole collection of people with varying styles. That really improves the accuracy. If you're only training on one person and then you try to apply it to someone else, it's not going to work very well because of that nuance, that difference in how each of us write, speak, etc. I already touched on a few of the classic applications for this, certainly check writing and fraud. The FBI uses techniques like this to track down fraud. Digitization, so both digitizing records that you may have, printed records, particularly in like law firms where they're dealing with warehouses full of old legal documents that they must retain, especially things like wills, those types of things. They have to retain them, but can they digitize them and save that space and money? And then in the digital humanities, so think about all of the printed books, the printed word out there that predates computers, which is pretty much most of human existence. How can we get those into digital form and therefore really make those documents alive again? Now, personal productivity, one of my personal favorites is Evernote, but there are other options out there. The ability to handwrite a note into one of these applications and have it be searchable is huge. It just makes it so much easier to go from written to digital, especially if you're not as fast of a typist. Now, another place with a lot of sloppy handwriting and lots of paper records that could really stand to be in digital form, the medical profession, health records, things of that nature. Starting to get more digitization, what I call native digitization on the outset, where you have them entering into the computer in the first place. But again, if you're in your 30s or 40s, you likely have 20 years or 30 years of medical records that are still handwritten. We're going to switch over to speech now, and there's two modes. The more common that we think of, which is speech to text, so taking the spoken word and converting that to text. We'll talk about that first, and then the reverse is going from text to speech, so speech synthesis. Now, in the speech to text, it's a very similar challenge and approach to how we handle handwriting. It's just we're dealing with different features. So we're taking speech, we're pulling audio signals out of there, and then we're constructing sequences of letters into words and words into phrases and so forth based on the signature of those audio features. And a key here, because a computer, like a human, we're not born with the innate ability to understand speech. We need to be taught. So do these machines. And it takes a lot of teaching, much like it takes a lot for a child to learn how to speak. We have to train that with sampled speech, matching text. That can be done interactively or with allotted samples sort of saved off and run through. Key point here, this is hard. Give the computer a little bit of a break. It took humans many years to develop this technique. It takes computers quite a bit as well. We have an incredibly wide range in terms of how we talk, our inflection, high and low, and the meaning of that inflection and pronunciation, which varies region to region, country to country. You have cultural differences. There are all sorts of things, and then obviously multiple languages. So you're dealing with a wide variety, and that is difficult for a computer to handle unless it's taught. So it needs a little bit of patience to get there. Now, we pretty much know most use cases that I'll talk about here because it's the obvious ones, the speech to text as it relates to Apple's Siri or Google's competitor or Cortana on Microsoft, where one of the key functions is you simply hit a button, you speak into it. In theory, it dictates what you say and can go out and do a search or something like that. Still a lot of error proneness to it. It's a challenge, but it's getting better. The more it trains, the more it learns, the better it will become. Now, dictation, which has been one of the classic use cases for this, more in terms of dictating meetings or court appearances and so forth, certainly a use case there. More recently, in the call center kind of approach or the automated system for handling inbound calls, and you're seeing these conversation bots where they're starting to turn speech to text to use that as a jumping off point to entering in with a conversation. Entertainment, particularly in the gaming space, is a very big, booming business, so it's worth mentioning here. And certainly speech to text and the reverse of that, the text to speech, are critical in creating more immersive interactive games and certainly virtual realities and augmented realities. And finally, it's worth noting in the media space, YouTube is an obvious one. Any media outlet, your CNNs and such, they are using technology to convert and create transcripts of their work and doing that automated instead of paying a transcriptionist. This is the flip side of that, which is taking text and converting into something that we recognize as speech and having it not be a halting computer voice. How do we train it to have better inflection and sound more natural? Training is key here. The approach behind the scenes is they're taking the text that you see and not actually treating every word as a word, but breaking it up into these phonetic sounds. And once you do that, then it's actually easier to piece together speech than it would be to try to record or train every individual word. The intonation, the timing, how to get that sounding more natural is where deep learning comes in. Synthesizers have been around a long time. Again, you probably think of it in more of a humorous light because it is not very good, but the technique is improved considerably when we start layering in ability to learn higher order patterns. And those are the style, the differences, the nuance that we humans think of as natural speech. Same use cases here, just on the flip side. Siri talks back to us. That's using this text to speech. Call centers, gaming as well. Let's talk nonverbal communication. The majority of our human communication, particularly at sort of the empathy level, the significance, the emotions, the posturing, all of that is built into our physical space without ever saying a word. If you're like me and work virtually or remotely or with people in other offices, it's so much better to meet in person than it is to have a phone conversation. You get so much more out of that interaction. And even video, it's not quite the same. So again, it carries this significance and it includes all sorts of things: eye contact and posture, how we gesture, how we move in the space. And because it is so much movement based, most of this is really image and feature detection coming out of a video stream. So we already talked about extracting features out of images and videos. This is an extension of that work into the physical three-dimensional space. As before, we can learn on known examples. That's one approach, but more powerful, more likely, especially with something like this, is so much of nonverbal communication is not a simple equation. It's more complex than that. So a computer could learn, for instance, when it does something or when it says something, people tend to roll their eyes. Then this is the outcome, and then they know maybe I shouldn't say that again. And it also can help with a trainer, sort of interactive training, providing cues back to the system. This is how we learn, right? We're constantly looking to our parents for feedback, particularly in the nonverbal space when we're first learning how to communicate. So there's some interesting applications here, and not the most obvious ones, but they're intriguing. One is virtual presence. One of the banks in the area where I live actually has converted at least some of their banks from having physical tellers in the location to having them in a call center. That's great, but in that video interaction, it's more difficult to get the nonverbal cues. And so a system could be used, and I don't know if they use this, but they could use it to analyze your posture as you're standing in front of your teller, this machine here, and it could say, I'm sensing agitation, I'm sensing aggression. Maybe I want to anticipate that, react to it, contact a manager to come over and provide some additional attention. So there's things like that that can help human to human interaction when the physical presence is not there. This gets into some controversial areas where these algorithms can look at nonverbal communication and pick up things like aggression or lying or things like that. So these are modern day equivalents of our lie detectors of the last 50 years. Is that legal? Is it ethical? Is it admissible in court? Good questions, no easy answers. But you're seeing these kind of technologies emerge that are using it in the security and the defense and the criminal justice system. And how do we react to that? That's something that we will need to figure out as a community, as a culture. And this is a lead into what we'll be talking about in some of the next sections, is interaction of people with robots, machines, and how they can detect our nonverbal cues will be critical in having a more natural and empathetic relationship between the two, as opposed to us thinking this is a nuts and bolts machine that we're simply interacting with on a transactional basis. So we'll talk a lot more about that when we start looking at robotics. So this is for you to think about what touch points in your organization are the most significant in terms of interacting with other people. And this could be person to person, it could be virtual, it could be people interacting with your systems or even with your physical presence, your brick and mortar stores. What are these touch points that you see and how could they benefit from either assistance or automation? It doesn't have to be full automation. It can be, again, assistance, decision support. Second one, the large volumes of non-digitized text or raw video and audio content. Think surveillance or survey cameras if you're in retail. Think old records. Are there valuable information in there? Are there notes from some of your past 50 years that are handwritten by your scientists that could contain a nugget of the next blockbuster drug or patent or technology. Think through those. We'll come back and wrap up. We covered 4 different areas: handwriting and text recognition, speech to text to speech, and nonverbal. All of these operate in many of the same ways. They're effectively using our deep neural networks to make predictions or classifications or basically constructions from one direction to another. And we're looking at handwritten images or text. We're looking at speech, audio signals. We're looking at video signals, effectively doing the same thing. And they touch on a wide variety of this human-computer interaction domain, as well as things like finance and medical records, all sorts of use cases. We're back and talking now about abstract thinking and emotions. Really, what we're doing is moving beyond the concrete. A lot of the examples that we've been looking at and the applications have really been more in the concrete world or the traditional world of computer programming and handling, where we're dealing with discrete data. We're trying to come up with trends and patterns, but it's relatively straightforward. We're still operating sort of at that lower level of detail. We're going to now move up the chain and start looking at more abstract thinking and specifically symbols and how we correlate concepts to tangible things. So if you think again of the example that we used earlier about seeing an A and a plus, traditional approaches and even some of the earlier neural networks and deep learning could identify the letters. They could identify that plus as a symbol. They might even identify it as sort of a phrase of an A plus. But newer techniques would then correlate or associate that to the concept of doing well, of an achievement, of an award. When we think of the two, concrete versus abstract, with concrete, we're dealing with this direct physical experience, the things that we touch and feel, or by extension, the things that the computers are processing directly, the inputs that they're receiving, whether it be because we're giving input to them or they're experiencing it in the world. And the kind of thinking, the prediction that comes out is very linear. It's logical. It's if-then kind of statements. Now, by contrast, if we think about abstract thinking and we think about how kids learn and go from the very literal to understanding these higher order ideas and concepts, and particularly around symbols. When we think then about predicting outcomes, coming up with novel connections, things that we might not have anticipated. And it's through these loose association of ideas or connections across concepts in different domains. So how we can manage this through deep learning is more content, better content, and a deeper neural network. So on content, what I mean is using a richer set of content, loosening the reins a bit, giving the computers more to work with, more variety to work with. So don't constrain them to a particular universe or domain. If you're training something for a scientific purpose, give them works of art on literature. If you're focused in medicine, focus on different domains too, like supply chain management. It's these associations across very divergent fields that yield some of these abstract thinking, these innovations that we think of. So broaden the content set and then relax. Relax the algorithm's constraints. Don't force it into a particular outcome or way of thinking too soon. And there are ways, techniques in these algorithms to sort of let it be a little bit more free in how it builds these associations between concepts. And then lastly, we talked about this quite a while ago in the introduction to deep learning. Let it build these increasingly deep neural networks. As much as hardware and software and time expenses we can provide these capabilities, give them more so that they have time to work out these more abstract patterns. So these are different applications now because we're able to start emulating, in some cases actually applying the same mental faculties that we do to a variety of applications in the real world, things that we would traditionally think of as human endeavors. Obviously, human-computer interaction, as we talked about with Siri and others, when you combine this kind of abstract thinking with the ability to handle speech and other communication inputs and nonverbal cues, you get a very powerful combination when it comes to having a more natural conversation with a computer. Certainly gaming and media in general, applying that for the entertainment industry is a very big deal. We talked a bit about using computers to generate articles for news and things of that nature. When you start getting into abstract thinking, then you're talking about literature and you're talking about other forms of writing, essays, opinions, things of that nature that traditionally, again, have been the auspices of just humans. Now, bringing it more to a commercial sector, this is where I start getting nervous because this touches into my area. One is in R&D, so thinking about innovation, invention, patents, that space, and doing derivative works, combining ideas to come up with new ideas. There's a lot of potential there for the people, the groups that can harness this capability to generate new insights and new business models out of that. And lastly, management, strategy, consulting, these kind of things that are divergent in thinking. You're combining ideas, you're generating new ideas. Let's talk emotions and feelings. For starters, there's no clear definition. You ask 1,000 different experts for a definition of emotions, and even they cannot agree on one. But for this purpose, we'll use the most general or agreed upon one we can find, which is it's this reaction or state of mind. So it's not just ideas or concepts like love and hate and things like that, but it's actually this visceral kind of reaction, either positively or negatively. The reason I bring that kind of visceral reaction up is this goes beyond traditional sort of brain function and thinking, right? You can't think your way out of emotions often because it includes more than that. It's hormonal and chemical reactions, it's neurological, it's biological in nature. We can't divorce the biology of it away from sort of the mental faculties. To some extent, computers being what they are, they don't have that same kind of biological composition right now. So to think that computers would necessarily feel and have emotions like us is naive. We can't compare the two. But in a more tactical, more practical way, what we can do, particularly with deep learning, is recognize and associate these human emotions. A computer, if they can tell when someone is upset with them or with someone else or is happy, that's useful. And then, as we did with speech to text and text to speech, there's a synthesis component. So, how can computers, even if they can't necessarily feel these same kind of emotions, can they emulate them, particularly responses? And we'll talk about use cases for that. In terms of approach, similar to learning more of these abstract concepts, but then with a very specific slant toward the emotional side, looking at what's often called in this field sentiment. Looking at the sentiment of an article, is it positive or negative in tone? Does it evoke anger? Does it evoke peaceful feelings? Things of that nature. So understanding what words, phrases, sort of trigger words apply for particular emotions. And then again, certainly with images and video, we talked a bit about this in human communication and nonverbal cues. Those come up again here because certainly different facial expressions and posture and so on have a great deal of information about the emotion that someone's feeling. One of the more famous emotional psychologists, Paul Ekman, did a study first in, I think it was the US and Brazil, maybe Portugal, but he did a study in Western cultures and found that universally people would identify the same emotion for the same facial expressions. He then said, well, maybe it's Western culture's influence. He went to Papua New Guinea, found a group of people that had never been exposed to Western culture, and with a few exceptions, they universally identified the same emotions. What's good here, and why I mention that, is that's positive for computers because that means they just have to learn one set of emotions, right? If they can read an emotion based on a training set of people in the United States, generally speaking, that applies around the world, especially with these sort of base emotions of fear, hate, happiness, those types of things. So what we do is we gather these features, we tie them to these particular emotions, either by giving the computer a training set or providing feedback as they go along, sort of this interactive approach. We're moving beyond the concrete to abstract, and then emotions are really a specific flavor of abstract thinking. And so the same kind of loose connections, deep neural networks, very important here. Emulating emotions, very similar to our speech synthesis, where we first identify the correct emotion and then we train our algorithms on how to respond to those. And this is often really a mirroring exercise. So if a computer detects that someone is happy, particularly a computer can say things that enforce that happiness, or perhaps a robot can actually do facial expressions that emulate the happiness features that they have seen. Sometimes that's consolation, right? If it's sad, then there's certain activities we do to try to cheer people up. So the same thing applies here. And like speech synthesis, there's an identification portion, and then there's a generation portion where it says, when I see this, I do these things. Applications here, very different. We're touching into a very different world. But from a business perspective, there are still applications because we are humans. We're doing business with other humans. There are obviously many, many touch points every day that we do either internally in our organization or externally with our customers that can benefit from this. So if you think childcare, care for the elderly, there's a lot of emphasis in research and even now commercial applications in this space. Think of PTSD relief for veterans. So there's lots of different pockets of health and care that can benefit from systems that actually better understand sort of almost a bedside manner for our computers. And lastly, in robotics, very key, particularly on this ability to recognize and mirror and emulate emotion back, is critical for these caregiving robots or robots that interact with humans on a day to day basis. So let's take a step back for a moment. Again, this one is a little bit more difficult to find that connection back to your own business, but it is there. First, think through management functions, strategy, R&D, financial planning, those types of activities that involve certainly higher order cognitive skills. We're not talking about automating routine tasks here. We're talking about the highest echelon of critical thinking that exists in an organization. Ask how you can augment what you're doing by these deep learning techniques. The technology that you have deployed right now, how could you benefit from that technology being more empathetic? Think about your call center conversations that are going on. Think of chatbots. Think of these things that you might have going on in your customer service organization. How could it benefit from a better understanding of human emotion and emulation? So we covered abstract thinking, where we're looking at these deeper, more loose connected neural networks, and we're training that with a much better, more diverse set of work. And that's applying in areas like human computer interaction, journalism, and the like. And then we talked about understanding emotions and emulating those emotions, where we're using text and we're using our nonverbal cues from images and videos to better understand the sentiment or this feeling coming from collections of features. And we're then pairing that and mirroring it up with an appropriate response. And that obviously applies for care across the spectrum, human robot and human computer interaction. We have spent a number of lessons talking through a variety of ways that computers respond to our input, things that we're interested in learning. We're going to turn that on its head and actually talk about creating original work. And in its essence, the question is, what does it mean to be creative? We tend to go to both strategy and sort of problem solving and the creativity that's involved there, but just as often art and music. And we think of these things as fundamentally human. And every time that a computer program or even an animal sort of approaches what we deem as being uniquely human, we move the yard line and say, because that's being done by something else, that's not human. When do we acknowledge that art and music and even theater can be created by something that's not human? What if I told you that those three pieces there, that painting, that song, or even an entire musical was generated by computers? What does that do to our sense of reality? How do we handle that? We're not going to go too much into the philosophical on this, but I raise that as a question because that's one of the challenges that you will face is that inevitably we will hear people will always be able to do it better. And what we're seeing, especially with this resurgence of deep learning and resurgence into neural networks, is really bringing that fundamental question into challenge, into light. So let's talk about how computers actually do this, because it is pertinent when we think about applications in industry. It's really an apprentice model, right? And we shouldn't denigrate a computer for having to go through an apprenticeship for learning these things, because the greatest masters have had to go through the same approach, right? You have to learn from someone.
Computers are learning examples, usually in one genre. So if you want to create an impressionist piece of art from a computer, you train it on impressionism.
But also weaving in other genres does help. It adds in that additional element of divergent thinking that helps in creating original work. We don't want to just replicate what others have done. We want it to be unique. What it does is it extracts what it considers key elements. Those could be features, it could be ideas, it could be different elements of artwork, and it combines those into new work. And just like an apprentice and just like some of the other algorithms we've talked about in the past, it responds, it adjusts based on the feedback it's receiving. Is this good work? Is it not so good? Again, the deeper the network, the looser the connections between the features it finds, the more creative we're going to think of this work. And if you think you view as perhaps the most creative works, whether it be art, music, et cetera, it's because it did something different, something unexpected. And that's exactly what we're talking about here. What we're finding is that in a variety of what we would consider traditionally the arts and media, writing, increasingly fictional work now, not just nonfiction and journalism, TV, movies, music, art, we talked about and showed a couple of those examples. But you're seeing computers start to both assist the artists in these areas and increasingly take over portions of that work. If you're in 90% of the rest of the business world and you don't deal in the arts or media, then you might wonder, where does this apply? How does this apply to me? There is a story. The first non human board member of a board of directors. This is a company out of Asia that deals in financial space, sort of financial investments and futures and such. And the algorithm, the system that they use, is so important in driving their business that they actually use it to help influence decisions on the board. And they'll eventually give that computer voting rights. So nothing is safe from that standpoint. If we think about the strategic work that many of us leaders and managers do, we might argue that there's something special and unique about that, but we're really drawing on a wealth of experience we have, our intuition or our gut, which is really, again, those loose connections. We're tying in ideas from disparate areas and we're making decisions. Computers can do that too. Key points on this, and we need to cover a wide array of work, and that needs to come from different areas, different genres. We train mostly on the genre that we're interested in. If we're doing strategic management, we're training it on strategy and management literature. We're training it on decisions we've made in the past. But we want to sprinkle in very different contexts like history and psychology and society that should influence those types of decisions. And again, we're building deeper networks and looser connections. So literature, art, music, but media, innovation, and strategy too. What I think we'll find is that increasingly roles that we felt safe, the highest order of thinking in terms of art and strategy and leadership, we will find applications very soon that will start eroding the uniquely human aspect of those. These are opportunities. Think how much more efficiently businesses can be run when we're combining the creativity and the unique capabilities that we have as humans with a lot of those same capabilities being augmented by machines. So this closes our set of lessons on computers in this cyberspace and this virtual reality of software and interfacing. So if you are someone that works in a company that's largely dealing in the physical world, you're thinking it's about time. We've spent a lot of time talking about how computers and these deep learning algorithms can work and learn in a very virtual or contrived space. We're dealing with data points. The reason that we started with those and why we are now jumping to physical environment is that a lot of the techniques and a lot of the skills that we talked about in prior lessons apply here as well. It's all of the same underlying technology, just with new data and a little bit of a twist, because we're going to be throwing a lot more data and we're throwing time and uncertainty into the whole equation. So in the next set of lessons, we'll talk first about how computers sense their environment, work in this massive influx of data that is the real world. And then we'll look at how they can actually move, physically interact with and move around in that environment. And then we'll wrap up by talking a little bit about how computers deal with overwhelming uncertainty, something we as humans tend to be pretty good at. How can we make our computers, our learning algorithms, better at it as well? So the challenge is data. With the real world, if you break it down to its most raw set of elements, it is overwhelming to think of how much data, how much sensory input we get. If we consider sight alone and look at two still photos of a couple of different crowds in different contexts, it's overwhelming. The number of faces, the number of colors, the shades, the textures, the languages that we're seeing and how to decipher those, the depth that we're seeing. So all of those things that we as humans have both evolved over millennia to be able to handle, but also learn through the course of our childhood how to manage. And we'll talk again more on the uncertainty aspect later, but right now we're going to talk about how computers handle this information and turn it into something meaningful. These algorithms aren't working in a pristine vacuum. They're working in an environment where they can make life or death decisions. If algorithms and robots can help detect a human in a fire and the best route to get there for a human or a robot to go and save that person's life, real impact. So there's a lot of opportunity here for the businesses, the people that can get it right. So what does that look like in practice? If you've heard of this term Internet of Things or IoT or anything about sensors, this is where deep learning meets sensors. They have to get this information from somewhere, and they're doing that from a variety of sensors. So video, which is giving you the visual aspect of things, both in terms of imagery and movement. but also haptics, so the touch, so the sensation of the environment. Things like the location and orientation, which way are you receiving these inputs from? Certainly audio, as well as things we don't think of like olfactory and smell, getting that sense, which is really analyzing chemical signatures. One of the revised is that these algorithms can handle things that we can't sense. Infrared, ultrasound, X-ray, all these different kinds of signal inputs that we as humans just weren't built to process. We have machines now that do that for us. Those are inputs as well that we can look at. Massive data, so a whole set of new technologies are being invented just to handle really the raw input and processing, let alone extracting meaning out of it, but just literally handling the volume that's coming into these systems. Now, from there, same techniques we talked about. So we looked at image extraction before, we've looked at motion and video, we've talked about sound and speech detection. All of those are the same exact techniques that we used in some of our prior lessons. We're adding in some additional capability to handle things like depth and proximity because we are interested in this three-dimensional space. We need to understand that. And we also need to understand more about objects, even more so than we were interested in initially, because we're going to interact with them. We need to understand what they are, what they're like. We need to be able to generalize, and we need to understand threats and opportunities. And again, just like before, we're using these deep neural networks to learn and not just identify the patterns, but then make predictions, right? We talked about making predictions, making recommendations, understanding sort of the statistical significance of getting a good set of outcomes or the best that we can. Same applies here. Just the ability to sense the environment has led to great safety improvements in transportation, braking assistance, parking assistance, notification of events around you. These kind of things are really built on this ability to learn what is a threat and when and what type of actions should be made. Really, that's the stepping stone to some of these driverless car concepts in transportation. Now, certainly there's a defense and a military, but more of a public safety, really. And it's as much detecting threats in the environment and understanding how to neutralize those. So this is where some of that smell, olfactory, sort of the chemical analysis comes into play. So being able to detect, even if it's not, so it's one thing just to do a match, right? And say, well, in my database, I know that this chemical is dangerous and therefore I'm going to do something about it. But being able to predict that it is, even if it's a new substance or a lowered concentration than I might have thought. So the ability to handle that uncertainty is important. Lots of applications in that space because, again, these machines can both go into areas that would be not safe for humans, and they can also then be additional eyes and ears for senses that we don't operate in. Another application goes more into commerce, particularly brick and mortar, because we're talking physical spaces. Amazon just recently announced Amazon Go, which is a fully automated store, and it can detect what you purchase, what you walk out with, and handles all of that transaction for you without ever interacting with a human. It's doing that through a lot of these sensors and understanding the variation, all the different orientations that could be picked up, how it's put into a basket that can be different, sort of oriented around. It's probably using RFID tags or something like that to know what's left the store, but it's handling all of this information in a real environment. That obviously will have significant implications if it broadens its use beyond this one use case or particular store. Let's turn this exercise around a little bit. I've asked you mainly to do sort of brainstorming exercises up till now to think about implications to your business. I'm going to make it more assertive this time. I want you to list the top 2 or 3 physical touch points in your business. These are places where people are interacting with things, things are interacting with things, stuff is happening. Not finance, not HR, not software. We're talking about physical customer touch points. For each of those, I'd like you to identify a potential project that will either improve the experience or the safety for each of those touch points. Quantify what that savings translates to. Is it improved efficiency? Is it reduction in workplace accidents? Tie it into some concrete terms and then come on back. So we talked about this physical environment and how we're dealing with this stream of data. So we're taking all of this data that's coming in from a variety of sensors. We're extracting those features in real time, and then we're correlating patterns that we're discovering across all of these sensors. So it's not just that we're looking at video or audio or smell, we're combining it all together, just like we humans do. Lots of applications here. We looked at driving assistance and safety, first responders, military, crime and terror. We've looked at that one before. And then also retail and supply chain management. Now, this is just relatively passive. We're talking about plopping some sensors in place and having it do something for us. Next up, we'll be looking at moving and how machines are learning to move in the real world. We last looked at how computers process information coming in from the real world. Now we're going to look at flipping that around. How do they then take that information and use it to navigate in a three-dimensional space? Robots are not new, right? They've been moving in the real world for some time, but they've been somewhat limited. They've either only worked in very constrained spaces where the environment was well known, or they operated on sort of the same paths and it was up to people to get out of the way, right? If you think of the old mail carts of the 80s and 90s. Things have changed and they've changed dramatically very quickly. And that's because of these deep learning techniques. We're able to understand nuance and abstraction and complexity much better than the machines of the past generation. That's led to things like driverless cars, capabilities like that, both military and domestic and civilian. This spans the gamut of anything where we have to take action in the world. A computer driven robotic or machine like this can come into play. So let's look at how that happens. We already talked about the input streams. Those are just as important now in these sensors and feature detection. But we're adding a new layer, and that's because the time element, not only are we anticipating how things shift around us, we're then using that information to move. And when we do that, it changes that model. So there's a constant feedback loop that we as humans use. Machines use that feedback loop as well to understand where to move, how to handle things like objects in their way. So a lot of this comes down to techniques around route planning and optimization. If you think about Google Maps or Apple's map programs where they're constantly figuring out if there is a blockage, an accident, how they can route you around to get you to the best route quickly. And there are things around obstacle detection and avoidance that handle that. Now, the key piece here that I talked about is that deep learning, it helps us manage this complexity and the uncertainty in particular, which we'll touch on even more so in the next lesson. A lot of the same techniques. We're just extending it out into movement and interaction that we didn't have before. So, what does that look like in practice? Transportation. So, when we think of driverless cars, we're often thinking of cars, right? Our own personal mode of transportation. But when businesses think about this, they're thinking about it in terms of transportation. And you think about the amount of money, time, safety that goes into relocating freight, whether it be on land or in air or overseas. These are things that need to be choreographed. Increasingly, we're seeing computers are getting better at doing that. So there's this notion of this European truck platooning challenge, which not only takes driverless trucks to the next level, they're not only interested in a single truck, but they're interested in these caravans that can travel together at very close distances and be fully automated, such that it is far more fuel efficient, there's less drag, and it's also safer and lower congestion because they're packed more tightly together. So we're seeing transportation as being one of these key applications. Similarly, if we keep on that industrial theme, mining and the exploration and exploitation of natural resources, huge potential market here because we're dealing at large scale. Very important as you think about the next, say, 50 years of resource exploration. We talked a little bit about the mail carts. If you've ever worked in a place that had those back in the 80s and 90s, they've evolved considerably. So, certainly, any kind of delivery service, whether it be drones, what Amazon and others are looking at, or whether it's the mail, as is this case with the robot here in Switzerland in the top right, seeing delivery being achieved through automated means, obviously, another key application. And then, certainly within warehouses, go back to this sort of supply chain and managing of fulfillment. These are increasingly being automated. We're seeing an explosion of these robots that are helping with everything from transportation to delivery. There's certainly a military and a defense component to this. We can either put machines into harm's way or into areas that we just humans can't survive well in. And we can do so both at cheaper expense and also a lot safer. So when we think about military deployments and thinking about bomb sniffing robots and entering into dangerous areas, drone flying for planes, and we can think of even heading to Mars and elsewhere in this exploration. Whenever you think of difficult, challenging, first mind goes to robots. Those were typically robots guided by people. Increasingly, they're becoming autonomous. Sports and soccer, if you've ever heard of the Robo Cup, increasingly we're seeing robots begin to emulate and interact with human movements and how they can do so, not just to compete in sports like this, but increasingly to be caregivers. to help the elderly, to help the sick. And we talked about a little bit of that when we looked at how these deep learning algorithms can understand and emulate emotions. I'd like you to think through those physical touch points we talked about last section. And now we're going to add in movement. We're going to allow our robots to move around. I want you to list 2 to 3 meaningful tasks that could be accomplished by these autonomous robots now. I'd then like you to do a more complicated calculation. So if you've done return on investment before, doesn't have to be overly complicated, but just think of the benefit, so the revenue or the productivity savings or the cost savings that are associated with this robot, and then assume a cost of, let's say, $25,000 in the first year, say about $5,000 per year in upkeep. We're increasingly seeing these kind of robots cost about that much, maybe even less. In 5 or 10 years' time, we could see that number go down to 5 or 10,000. So it becomes a very realistic cost to pay for some of the benefits that you can reap. So take a few minutes, think through some scenarios, jot down some numbers, and come back and we'll wrap up. When we're dealing with movement in this physical space with robots, what we're seeing is that these deep learning algorithms are helping handle this massive stream of data we've got coming in from sensors, handling the uncertainty of movement in that space, and constantly doing this modeling and planning and replanning as they work around obstacles and other challenges. Before, robots had to be very sort of live in this simplified environment where they had clear directives and clear routes. And anymore, they can now handle a lot of that uncertainty through these algorithms that we've been talking about. So, obviously, transportation, delivery, supply chain, that whole ecosystem is being transformed by these technologies, mining and natural resource extraction, and military and defense. Any harsh environments, as we talked about, and then even entertainment and sports, where we have the potential for interaction between humans and machines in a very real manner. Healthcare, treatment, and care for the elderly and things of that nature all sort of bundle into this human machine interaction. We've now reached the end of our survey of use cases and applications in deep learning. We'll be looking at how all of the different pieces we've talked about tie together when we start thinking about uncertainty. We'll walk through this course, and then next we'll be looking at how you can bring all these different types of use cases, applications into your own environment, into your organization. Talk about some of the challenges of getting buy in, overcoming objections, things of that nature. Let's dive into this notion of uncertainty. And what it really means is we've looked at all of these different techniques that work for fairly constrained problems. And even when we were looking at the real world, where we're dealing with a lot more data, we're still working on maybe 1 or 2 constrained problems like movement or driving, answering questions, things like that. What makes us humans so unique in the biological world has been our ability to generally problem solve, the ability to really have this executive function that controls all of the other aspects of our life and to be able to react quickly, to predict, to do all of these things that we do so much better than other animals. And what we're finding is that computers can model some of those same executive functions. And that's really what we talk about handling uncertainty. How do we handle it? Well, we guess. A lot of the times we actually guess. We often think we're being more clever and logical than we really are. But what we're doing behind the scenes is we are evaluating all the options that are in front of us, and we're making an educated guess. We're making a prediction about what the best outcome will be, and then we do it. And then we see how it turns out. And if it doesn't turn out so well, we course correct. We, I think, sometimes give ourselves as a species a little too much credit in that everything is purposeful and done with clear foresight. When in reality, what we do and what helps us is we relax some of those constraints. We allow ourselves to be wrong. We allow ourselves to make these predictions and see how they turn out. We also are very good at convincing ourselves that the path is correct, and we reinforce some of our mental models to be in sync, to be harmonious, to allow ourselves to think that we were correct in the first place. What we're finding is that computers can start to model that same behavior when we take these kind of deep learning techniques and we take it up a level. But we do that across a whole host of algorithms, a whole host of inputs, and really use it as more of a general intelligence function. Now, there's a story here that goes back to the 1990s when Gary Kasparov was playing the computer Deep Blue, the chess competitor to some of the world's best chess players. There were a number of matches, they did a number of rematches and such, and in the end, the computer bested this world chess champion. But it wasn't so much the raw computing power that was Kasparov's undoing. The computer could calculate, millions of moves and such. The brute force was what allowed it to play initially on par with Kasparov. In the rematch, Gary actually was unnerved. And he was unnerved because toward the end of a match where he was handily winning, Deep Blue did something unexpected. It made a strange move, a move that he hadn't anticipated, and it completely threw him off his game and ended up losing the match. Now, in the end, it's unknown. Was that a mistake? Was it a glitch in Deep Blue? Or was it something else? But it's that notion of being able to anticipate, try, predict, make these changes, and then react to that. That notion, that feedback loop is what's critical. And what's so telling of this story was that that's in many ways what we view as intelligence. When we see that, when we see that thought process, we think of it as being intelligent. And that's what so unnerved Kasparov. So something to keep in mind as we dig into the nuts and bolts of handling uncertainty. So really, as I mentioned, this is about modeling outcomes and doing this in multiple ways with different algorithms. If we think about how we function as humans, we have lots of different ways that we solve problems. Computers can do the same thing. Key point here is that they estimate what the likelihood of success is, or whatever the outcome that they're looking for. And in doing so, they will pick often either the most likely approach, or what we've seen to be actually more effective is randomly selecting among the best options, adding a little bit of chaotic element to this so that it does have that element of uncertainty built into how it's picking things. The feedback loop, though, is the most important, right? It cannot simply make a prediction and then go about its merry way. It must come back and evaluate what happened. Was it right? Was it wrong? Was it partially right? Was there a better model? This constant adjusting and tuning is what is so key for computers to act less like the computers of generations before that were dumb machines following programs to something that is getting closer and closer to emulating true human intelligence. Now, what does that look like in the field? A lot of the use cases we've already talked about are getting better and better because of this increased ability to handle uncertainty. So if we think about driverless cars, driverless trucks, the more opportunity that those computers, those systems have to learn and to see different scenarios and to adjust and to predict and then see, what happens and then make another adjustment from there. That ability to sort of cycle through and learn has been critical to it continuing to handle uncertainty. So the next time something comes up, it can extrapolate. It can say, well, I've seen something like this before. I think this is going to be the best way to respond. We see that also in military and defense operations. We see it with transportation and supply chain management. Certainly in deep space exploration, the Mars rovers and space orbiters and things of that nature are increasingly being programmed to think and not being programmed for every eventuality up front. Now, this comes into play when we start thinking again about human computer interaction. The more natural we can make the interaction between a computer and a human, the more it's going to feel like a natural conversation. And the acceptance of that technology as something that's part of our life will get better because we will feel more like we're on the same wavelength. It doesn't feel natural yet, but it's getting there. And last, we talked a little bit about strategy and innovation. It's worth coming back to that because so much of management and strategy is working with limited data and making the best choice you can with a vast degree of uncertainty and certainly lack of information. This kind of approach of handling uncertainty works very well then in this very nebulous environment. A lot of the concern around jobs being taken from robots and from smart machines, a lot of it has been focused at, I'd say, more task-oriented work, and executives and others feel pretty safe that their jobs are secure. Won't be the case, and I don't think for very long before we at least start seeing technologies that help those executives, and those that can embrace it will do far better than those that fear it and try to shut it out. So wrapping up, handling uncertainty is all about this modeling of outcomes. So taking all of these data in across multiple algorithms, multiple approaches, aggregating that together and figuring out which outcome is most likely, what action will lead to the best outcome. And then selecting that and then reacting to that input and adjusting accordingly. And we just touched on a number of those applications. So you've learned about a bunch of different techniques and use cases and applications for deep learning, and you are ready to charge forth and conquer the world, right? Well, it's not that simple. Often the technology is actually the easier aspect of things. It's the people side of the equation. It's the buy-in It's the change management aspect of things that often can sink a project or can spell its success depending on who's leading it and the approach taken. Now, I've been doing this, as I mentioned before, about 20 years, and I have heard it all. I've been in both internal and external management, sales, and development roles. And the list of objections is a mile long. I put a couple of my favorites up here, right? We don't need that. We don't need what you're selling or what you're suggesting. It's too expensive. It doesn't work. We've tried it before, so on and so forth. You've likely heard these if you've really stepped foot in any kind of technology space. These objections will sound familiar even if you're not familiar with AI or deep learning projects, right? Because any technology project, you've likely heard some variation of the same themes. It's easy to fall into the trap of becoming confrontational about this, thinking about it's unfair that people are doing this to you and feeling just sort of isolated. And then as a result, becoming confrontational yourself. So becoming too assertive, trying to dominate the situation. And that, as you can imagine, rarely works. We need to start from a place of understanding that the root of many objections, it really boils down to one thing: fear of change. And even if you love change or think you love change, like I do, in the end, we as people are habitual. We are creatures of comfort. We enjoy things staying the same, the status quo. There's a certain comfort level in that. Certainly in certain aspects of our lives, even if we think we are very dynamic and flexible in other areas. And when it comes to people's jobs, to their livelihood, nothing can feel more threatening to that than disruption. So if we start from an understanding that these objections aren't personal against us, they might not even be related to the project itself. It boils down to this level of fear. What's the best antidote for fear? Understanding empathy. But if that were enough, then conversation's done. It's obviously not. What you need to establish is a pressing need. Now, there's this concept, if you've heard it in business, called the burning platform. It basically means standing still is not an option because the platform you're on is burning. You got to do something. You got to jump. Now, it doesn't usually come down to as stark of terms as that, but you can't go into building buy in for one of these projects simply on the fact that the technology is cool or everybody's doing it. So, of course, we should do this too. You have to tie it back to something that is either painful for the organization currently, and so painful they can't bear the status quo, right? They can't live with it. So it's got to be something they need to actively pursue, or it could be an opportunity that is so enticing that you can't pass it up. The more of a hook that you can get in, the more you can find the angle where this kind of technology will be disruptive, but in a positive way, and the alternative, the status quo, is really not viable or attractive, that's when you have a root of something that you can build on. So don't jump in with the technology or with the idea until you have the need identified. So let's say you have that now. You understand within your particular organization what it is that would really get people excited about embarking on a project. So what do we do next? There's going to be a lot of objections still, right? Well, that's fine, but no one else is doing this. Our competitors aren't doing it. It's too expensive, et cetera, et cetera. Rely on that social proof. Rely on the fact that others have tread ground before your organization. Very few people and even fewer organizations want to be the trailblazer, right? They don't want to be the first one to try it because it usually means it's a high risk of failure and it's more expensive. You don't want to be a laggard per se, but there's a term called fast follower. Most organizations and people want to be a fast follower. They don't want to be the very first, but they want to feel like there's someone on the cutting edge. So rely on the fact that larger organizations have already been doing this and have been doing it for years really helps. And these are name brand recognition, right? That you can use to say, we could be the Netflix of our industry. We could be the Amazon of our industry. But to a specific point, all of those organizations are very large, right? They have billions of dollars at their disposal for R&D. So it's really not a fair comparison. So you have to bring it back down to the fact that this technology, like all technologies, is becoming increasingly affordable. And you can rely on history to bolster your case. So Moore's law, as you're all familiar, it's the doubling of computing power roughly every 1.5 years or so. That has then been extrapolated out to really refer to the exponential either growth of capability or diminishing of costs on a wide variety of information technologies. It applies here too. When I started in this industry, the amount of hardware that you needed and the software really required millions of dollars of investment up front. Now you can use an API, an application programming interface, to connect to services to do this work for you. For instance, IBM Watson, they actually let you handle a certain number of calls into their services for free. So you can effectively build a rough prototype of an application and never spend a dime to get some of the same capabilities that used to cost these organizations millions. It's phenomenal. When you couple that with cloud-based platforms, if you've heard of platform as a service or infrastructure as a service, things like Amazon, AWS, Microsoft, and their Azure product, this allows you to spin up resources, crunch data, create an application in a fraction of cost that you would do if you had to do all that internally. And what's more is you usually don't have to get your IT, your infrastructure team involved and procure hardware. The cycle times here we're talking about are in hours, not weeks or months. Increasingly, we can also rely on built-in capabilities. Microsoft SQL Server, just one example where they have started bundling not quite deep learning, but more machine learning capabilities. Deep learning will follow, so that if you already own a license to this software, you get the platform capability of machine learning at no extra cost. And then, of course, there's open source programs, Python libraries like scikit-learn, Cafe from University of California at Berkeley. You've got TensorFlow, which Google recently released. You get all of these different capabilities that are now being open sourced and effectively, again, are free if you know how to install them and use them. So the last point, that consulting services really help here. You don't want to necessarily spin up an entire division of people that understand how to use the software. But for a reasonable cost, you can contract consulting groups to come in and do the work for you. They'll often bring their own tools. That is a cost savings as well. So you can especially get some of the early visible signs of success through projects driven through consulting resources. You can then use that model to bring that capability in-house as you get more experience with it, but it's a great way to get started cheaply. Next is a notion of a proof of value. Now, you may have heard of a proof of concept or a POC, and I've heard this term in the past couple of years and have really gravitated toward it. When we think of proof of concept, we think about things like assessing the technology, user feedback. It's almost like a little pilot that we do to make sure it's the right fit for the organization. And then if everything seems okay, then we move forward. But a backseat to that whole proof of concept thing is actually showing whether you're getting any value out of it. So the proof of value, this POV, turns that on its head. And the focus is on what kind of demonstratable outcome are you getting out of this capability. So you start small, you target it on a high value need. And the idea of the pitch to your management is basically to say, look, what do you have to lose? We have this burning need here. Other organizations are doing this. We can get a proof of value up, see if we can answer this problem, right? If we actually get something that the company can benefit from, and it costs 25, 50K. That's in organizational land, particularly for larger organizations. That's like supervisor manager level discretion for spending. It's a very small threshold and can get your foot in the door. It's a logical sell. It's something that's easy to contemplate, and it doesn't require going all the way up to senior level of management. So proof of value, think of ways that you can demonstrate this in reality. Our last step is then to build on this success. This is incremental. So avoid proposing this notion of a platform. Those are fatal words in this environment. What it resonates then with people, whether they're technical or business minded, is it immediately says, we're going to spend millions of dollars to build something that may help someday. It denotes this massive undertaking, mountains of resources, mountains of time that the organization is dedicating, hoping they can get something out. You'll never get to the point where you demonstrate enough value to justify the cost before the rug gets pulled out from under you. So think incremental, think phases. In each of those phases, just keep taking that core, that nugget of pressing need and expanding out and finding other high value needs. Look for these adjacent opportunities. So it might be applying the exact same approach that you did in HR over to finance or to over operations. And always use your past success to your benefit. We talked about external social proof. Use it as your internal social proof. Hey, did you know that Jane over in HR did this same project with us, and she's now realized a 15% reduction in costs? That kind of internal networking, and particularly if you can identify early stakeholders that are key within that internal network, that are influencers, the better off you'll be. Follow the money. Get as close to the money as you can, meaning Pressing needs are usually as close to either revenue generation or cost savings as you can get. There's usually a preference for revenue because you can always build more revenue. With revenue, the sky's the limit. In the last session, we covered some of the common objections that people have to really any kind of change, particularly with new technologies. This session is going to cover something that's a little bit different. These are concerns around ethics and privacy that are above and beyond some of those base concerns. And they have to do with the direction that AI is heading and some really valid things that need to be taken into consideration by us and addressed. So let's start on the ethics side. A real one that is as much a concern today as it ever has been is around job loss and displacement. And this is a touchy subject. We, as business people and technologists, can never isolate or wall ourselves off enough where we lose touch with the impact that some of our decisions have. At the same time, we can't single handedly or even as a group and organization stop progress, right? We are going to be a party to it, whether we choose to or not. This is the direction that society is heading and has been for the last hundreds of years, ever since automation first became a possibility. That being said, it doesn't need to be an inevitability, and there are certainly things that we can do collectively to help soften the blow of technology displacing jobs. The first is within an organization, there's always an opportunity to reallocate. And what I mean by that is not laying people off, but it's actually just finding ways to leverage those same people in higher value tasks. If you had someone that was originally working a call center and their job has been displaced by an automated machine, can you retrain them to, say, handle internal training? They have the same kind of people skills, that same customer service translated into a different role within the organization that might be more difficult to do. It's a great opportunity for them to stretch and to grow their careers. Now, if that's not an option or not an option for everyone, what we're seeing increasingly, we've seen it with robotics and some of factory automation, is that you can retrain people that are in this space and they understand the industry. They know the nuts and bolts of it, but retrain them for some of the higher tech jobs. Maybe they were a machinist before. Now they're maintaining the robots that are doing the machine work that they used to do. So that's certainly an option as well, wherever possible. And then last, what we will see is a rewriting of job descriptions of kinds of roles that you would have never dreamed of 20, 30, 50 years ago. For instance, all of these machines need to be trained. So you could find an AI trainer as a job description, someone that actually goes in and knows how to train systems in particular areas. Certainly anything in the technology and development space, AI consulting, there will be a host of jobs available that circle around this ecosystem. And it's very similar to sort of the green jobs that we have seen over the last 20 years as we become more environmentally conscious. But beyond jobs, this is an important one. It's hit into the news recently in many different ways. And it's this notion that we as humans, unfortunately, develop biases based on our experience, right? We have a particular lens to the world where we view things, and based on our experience, we're sort of trained to react certain ways. And this is much the basis of gender bias and racism and things of that nature. Well, a computer can suffer from that same false perspective, that limited perspective to think that that is reality. And what happens are machines that are vetting job candidates or vetting ads to be placed on a search result page because they're working on past data that also happens to be biased because it involved human factor. They're just replicating that bias. And it's a real problem. So, how do we handle that? One of the ways is we've got all these great tools at detecting patterns. Use those same tools here. Use them to actually monitor for and identify bias when it occurs so that you can correct for it. Another interesting addition here is using the ethics committee, which is predominantly in organizations been used to police ethical behavior of people in the organization. They can be retooled and revamped to also provide oversight of these increasingly intelligent algorithms. It can be viewed as a relatively radical idea, but it's not a far stretch. They're monitoring the same kinds of concerns, the things that we want people to do ethically, we want our machines to do the same thing. It's a nice overlap. Now, last but not least is what about this rise of the super machine, right? I call this the Terminator concern. It has validity from the standpoint that certainly some very bright intellectuals and people of our day, they do believe that this could be the eventual climax of AI progression. There's no easy way to say, no, that's not going to happen. What I can do is talk about a few of the ways that we can understand it better and prevent it. One is honestly to understand our own destructive nature. I am much more concerned in a practical sense of what we humans can do to each other and the terrible things that we can do in society. That to me seems like more of a real concern, but there's something underlying there in our nature that we should understand. And if we can understand that better, we can make sure that the next generation of things we build, these machines, understand that and operate in a different context, that they don't fall into some of the same fallacies, the same traps that we have. Definitely global independent AI oversight and ethics is important. You see some organizations like Google and Facebook having their own AI oversight. Some of them have sort of spun those off into different sub organizations. But what's most important is that they are independent. They're not being governed by the same organization that could benefit from AI. And then, taking all of that information, putting in some form of system failsafe, a safety switch, as it were, can be built into these things so that if nothing else, we have an option, an opportunity to trigger that. So let's bring it back a little bit more near term concern and look at privacy. Obviously, a big issue, obviously, something that's in the news quite often. There's two sort of angles to look at. The first is unauthorized human access to personal data. This could be an insider, an employee who is disgruntled and has access to these systems and can basically turn that information loose, a Snowden, for instance. Or it could be an external threat hacking that information and then making it public. Both are real threats. If you don't believe me, talk to your information security person. It is eye opening to understand how much of this is going on and how pervasive it is, particularly in corporate espionage. So, what can we do if you can anonymize your data? If you can get rid of the tie between an individual and the data of interest, particularly in, say, medical records and stuff, you've already won the battle. If you don't need to know who that individual is and you're more interested in understanding the trends, get rid of the who and you're better off. If you lose the data, if it gets stolen, it's no big deal because it doesn't tie back to an individual. Beyond that, strict information security safeguards, controls are a must. If you don't have an information security person in your organization, get one. They are worth their weight in gold because one incident like this, one slip up, can literally sink a company these days. So be mindful of that. Beyond that, as part of that security control, limit who can access the data and from where. So, what systems they have access to, from what machines they can use, whether it be from home or the office, and then encrypt, protect that data both in transit, meaning when it's moving from, say, your data center to somebody's computer, or from one data center to another, or from the data center to an algorithm, and then at rest, meaning when it's stored. And the last consideration is, do we care if a machine knows something about us? If that Netflix algorithm or Amazon algorithm knows what I'm doing, what I'm reading, that's a line we haven't really had to think about yet. But it is something we need to understand what that means. And again, sort of goes back to ethics as well. So, what can a machine know? Should we care? More than anything else, the ways we can sort of limit that concern is we can limit what the system is looking at and how it reports those out. So if it's operating more as a black box where its inner workings are never exposed in terms of data that you can get out of the system that someone can go in and inspect, then it's safer from that perspective. And we can also talk about just limiting who has access to it, limiting what they can see, and so forth. As you get into particular industries, you think of HIPAA and privacy concerns there. You think of race and gender, you think of education, you think of psychology and therapy and things of that nature. There's just a whole host of information in different industries that are spawning a new set of concerns around both ethics of using that data and the privacy. Just be mindful of that. When you embark on a project, don't neglect that because it can sink any efforts to get traction. So you've successfully gotten buy-in to start a new AI project. You're excited, you're ready to go. The battle is already over. It's not. It's not even close to begun. The mistake so many of us have made and continue to make in technology related projects is skipping to the end, assuming that once the technology is in place, it's easily adopted. It just sort of naturally happens. And that couldn't be further from the truth. I don't speak to this from some high horse on a pedestal. I speak from painful experience that I've made that mistake time and again. And I have finally figured out that it takes a lot of time and a lot of effort and a lot of active work to make technology stick. That's true with any technology, especially true with AI and machine learning related technologies. If you're familiar with Simon Sinek's work, he is a TED Talk speaker and author. And he's done a nice job of sort of encapsulating in its essence what organizational change management really is. And he calls it starting with why. And it's this notion that people don't buy things, they don't buy the what, they buy into a belief into the why. And this is true for accepting technology and other change too. We think that people should accept these things on rational grounds. This software will be better for you because, and we list our 5 reasons and we go on our merry way. In reality, it's much more of a visceral and emotional reaction. It's the psychology behind it. Why should I embrace this? Is my life going to be better? Is it going to be easier? What's the impact to me? What is the impact to people around me? And until we start with that, we're going to be beating our head against the wall, trying to figure out why technology projects fail without embracing that simple fact that we need to touch people on an emotional level. So let's look at what that means. Well, one acronym I've come up with and I use quite a bit in thinking through these things is TEACH. You need to be willing to invest the time and the resources, both from yourself and your project team, and understand that these things can take months, if not years, to germinate and have active effort. Many hours a week, reaching out, talking to people, reinforcing messages, communicating in a dozen different ways. One of my mentors and managers earlier in my career said, if you communicate about 10 times as much as you think you should, you are starting to get it right. So think that 10 times the time that you might think, and you're probably getting close to what it's actually going to take if you want to be successful. Now, next, we already talked a little bit about empathy, right? We need to come to people where they are. We need to understand their position, understand that fear that we talked about when we were talking about getting buy in the first place. That doesn't stop once we get that buy in, it continues. We need to empathize with our stakeholders, with end users. We need to understand how this is going to impact them and speak in their language. So come to them. We assume because we're so intimately familiar with the project that everybody else is too. We need to take a step back, understand where people are, and then bring them up to the same level of awareness so they understand what this is, why we're doing it, the benefits, what we hope to get out of it. All those kind of elements, they need to be communicated. Communication. As many different forums and tones and target audiences as you can. And these need to be targeted and meaningful. The blanket email to the entire organization once is not going to cut it. You go to each group, you tell them why it's going to benefit them. You do it in a tone and a voice that resonates with them. In fact, it's better if that can come from trusted advisors within that group. Lots of different media types as well. We're talking email, we're talking on websites, we're talking in person, town halls, webinars, any mechanisms that you have in your disposal, use them and be creative. A firm that I was at, we were launching a mobile app effort and we did a really splashy multimedia campaign that was actually unheard of. This was at a law firm and they don't tend to think in those kinds of ways. But it was highly successful because it was different. It caught people's attention. And lastly, help. This has multiple meanings. One is make sure you give them the help, the assistance they need to be successful in the change that's coming. Don't throw them the software and say, go figure it out. Putting up a one-page PDF quick guide is not enough either. You need to figure out different, again, means of getting to them in a method and a medium that works for them. So think online training, think in-person training, documentation. There's all different kinds of ways that work for different people. Let's look at some specific steps. There are many different OCM, organizational change management models out there for driving adoption. John Kotter is probably the forerunner of this from a variety of both an original article and then a book about driving change or leading change. It's the gist that's important here. You don't have to follow every step religiously, but it's intended to give you an idea of the things to think about. When we create the climate for change, this actually starts at the buy-in, at the business case level. You need to be thinking about these things as you're pitching. We already talked about them. Creating that sense of urgency. What's your burning platform? Forming a powerful coalition. This means finding people within the organization that are well placed to be influencers. You want those early champions. They're people that are going to help you when the going gets tough and not abandon you. Form that coalition and then create a vision for change. And this gets back to Simon Sinek's why. What's the to be vision? And think big, think in terms of stories, think about what's going to be different for people and how it's going to be better. So create that vision. Once we do that, we get into the nuts and bolts of this is the groundwork to go and sell the organization on why this is good. So communicate, Empower action means make it something that they can do, something that is active for them that they can get value out of. It's not just passive, like, "Oh, okay, new software got pushed to my desktop. All right, I guess I'll start using it." Give them incentive, give them some reason to engage. And then we talked about this in buy in, the quick wins. We talked about a proof of value. Find the quick win that will demonstrate to the organization this is worth doing. No platform plays here. Don't say 3 years from now, the world is going to be much better because the entire organization is running on ERP. It's not going to work. You need to find those quick wins. You need to find a division that's more receptive or a particular group and run with that, create that quick win. Even if you do all of this, don't quit. That's where, a change in management or project fatigue, because these projects can go on for so long, starts to set in and you sort of trip right before the finish line. So you need to build on that change. And I talked about that before about creating other quick wins. And then making it stick means making it part of the organization. So how can you entrench this so much into the culture that people never imagine that it could have been any different? It just becomes part of what you do. In your law firm, probably email, certain software like word processing, particular systems, particular procedures are so ingrained that you don't even really have training for it anymore. You just sort of assume everybody picks it up because everybody else will sort of coach them along the way. That's the kind of invasive cultural change that you want. If you don't embark on an AI project right away and you're just using this as sort of background information, hopefully this was useful to you because it applies universally. I've used it, as I mentioned, for anything from mobile apps to an operating system upgrade, as dull as that might seem, to much more flashy projects like decision support and AI related tools. So it applies really across the board. But there are some specific considerations for AI that we should take in. The first is factor this in. There's a lot of negative press, a lot of belief out there about the negative implications of AI. Even the term itself is loaded. Factor that into your plans. Similarly, know your audience's tolerance for mistakes. I happen to have had the pleasure of working in organizations where that tolerance is insanely low. I've worked a lot with lawyers. I've worked a lot with scientists and researchers, pharmaceutical companies, business people. Particularly lawyers are very risk averse and very intolerant of mistakes. They expect things to be perfect because, quite frankly, their clients expect that of them. And it's sort of built into and entrenched in the institution all the way from law school up through practice. The reason I mention this is that most people are not that tolerant of mistakes. There are very few that are more entrepreneurial minded, that are sort of on that bleeding edge, that are okay, they can accept some of that. But in general, assume that your audience is not, and that they will run you out of town if you have a very visible mistake early on. So, how do you handle that? Well, there's a couple ways. Treat these as decision support tools more than decision automation wherever possible. Even if it's intended really just to be sort of a human gut check at the end, the more that humans feel that they are in control of the algorithms, and even if they can tweak parameters that actually make no difference, they are more willing to accept the consequences, the recommendation of the algorithm. If people feel they have control, if you give them a button that they press and a lever that they can move around, that lever could do nothing, and they will still feel more in control and will be more willing to accept that. There have been studies published on this. I'm not suggesting you fool people into that, but give them some sense of autonomy, right? Think in terms of recommendations instead of decisions. Think about Amazon and Netflix. They're simply recommending. So it's just recommending items for you. You can take it or leave it. The same applies here in terms of building adoption. And lastly, put that human face on the interaction. Make it feel like they're interacting with a trusted colleague, and acceptance will go much higher than what it was previously. And we saw that with IBM Watson in some of their health applications where they're applying Watson to cancer research and finding that doctors were more receptive to IBM Watson's recommendations when it had a more human, collegial kind of interaction. Well, we've arrived at the last session of this course. A lot of what we've talked about would have seemed like science fiction 5 or 10 years ago, certainly 100 years ago. But it's amazing how quickly things have progressed. What that means is that it's going to be increasingly difficult to predict what the next set of things that seem like science fiction now, but will be reality in 5 or 10 years. Rather than just guess, we're going to take a look at history and look at rapid growth. And the reality is that we as humans are terrible at this. We are linear thinkers. We grew up in a largely linear world, and it's how our brains have learned to process and detect patterns. So, as an example, if you think of the concept of lily pads, these are those little green leafy things that form on ponds, and they're notoriously known to gobble up resources until they fill the pond. And the notion is they roughly double every day. So this is showing lily pads in a pond. If you start with two and you go from two to four and four to eight and so on, you keep doubling. After 25 days, the pond is about 5% or so full. So the question is then how many more days does it take for the pond to completely fill up? 5 days. So from that point on the 25th day, it simply takes five more doublings to completely fill the pond. If you were to chop off days 26 and on, it pretty much looks like a linear graph with maybe a little blip at the end. Our brains detect linear patterns like that so much more easily, and we notoriously either over or underestimate exponential growth. The same thing is happening on all of our different information technologies. And in fact, if we look at the history of technology from 1900 on, we can see a shortening of both the introduction of new technology. So we're introducing more and more quickly. And we're also finding that saturation is happening much more quickly. So the bar there is indicating sort of from the first 10% of adopters up to, I think, 75 or 90% of adoption in US households. And you can see it took almost 60 years for things like the stove and the telephone and the car to actually touch most US households. The tablet, the smartphone, the HD TV are measured in mere years. So, this rapid rate of technology adoption, of creation, they are things that we are not well equipped to predict. And so, we either go overboard, where you see a lot of hype and a lot of money thrown into something that's not quite ready yet, or more often is the case, we underestimate and we miss the boat. So, what does that mean with AI? Well, we need to look at deep learning in the context of a number of other what are called megatrends, right? These big shifts in technology. The first we've talked a little bit about, and that's cloud computing. So, Amazon Web Services, AWS, Microsoft, Google, they all have these giant data centers that they're now basically leasing out space to. This is transformative. If you are working in the technology space, particularly developing software or running applications, you know this to be true that it is a earth-shattering change in how we use technology and how we procure hardware. We go from cycle times of months to hours. So that's one big trend. The other is simply computing power itself. We are able to compute and store massively more than we could 5 years ago, and we will be able to do even more so 5 years from now. That will transform again how much we're able to analyze this data, how much we're able to build these more abstract patterns and keep getting closer and closer to human capable cognition. In addition, neuroscience and the ability to actually understand how the human brain works, we will be able to better understand what makes us tick and therefore make it easier to develop what makes a computer tick, what makes these smart machines work. Nanotechnology, there on the right, that is another capability where we're able to get finer and finer resolution capabilities, machines down at the micro level, and that will transform a lot of different industries and can even impact how we build chips that are doing deep learning type work. And last in the middle there, we will need to figure out how to power this massive thirst for information. These things do not come cheaply, either in the form of natural resources or energy. And no matter what your political stance is, the energy that we use today in the form of fossil fuels will eventually run out. It is a finite supply, and we know this. It will become increasingly more difficult, more expensive to get it. So, as part of any rational energy strategy, long term, we need to have a better source for more and more energy that's going to be feeding these things. Solar, wind, other kind of renewables like that, also yet to be even determined other sources of energy. In the very near term, something that we are already seeing and we're going to see a lot more of is just context and personalization. It still shocks me in most systems today how little of that we actually take advantage of. When we know who is searching, what they're interested in, what they might be doing at a given time, where they are, what the weather's like, all of these different factors, we can be so much more intelligent about how we serve up results or serve up answers than we could if we just ignored all that and looked at what the person asked. So, this notion of context is key, and it will be increasingly so in many different applications of AI. If you think of driverless cars, obviously the position is important, but the context of the road conditions, the weather, other cars, all of those factors need to be considered to have a holistic view of driving a car, much like we as people do. Not that much further out, we're already seeing inklings of this. This is one of the near-term applications. Smart everything, smart homes, smart cars, smart office buildings. So these are basically using deep learning kind of techniques and other approaches in making a device that used to be rather dumb or just inoperable to be something intelligent. We're seeing an influx of that when you hear of Internet of Things and sensors and all of those other kinds of buzzwords. Following the hype, there's a real potential there for basically embedding the same kind of technology cheaply into all sorts of different aspects of our lives. Personalized medicine is the next major revolution in sort of the healthcare space. If you talk to most doctors and medical researchers, we are still at our infancy of medicine. It may seem like we know so much and we have made such progress, and we have, but there's so much more to go because we don't understand yet much of what goes on in medicine, in metabolism, in the workings of the human body. Because we're dealing at that micro level and it's such a complex system, our capabilities of understanding that and researching it are limited. Now, if we can point powerful machines and nanotechnology into that space, our knowledge will grow considerably, and we will be able to use that to come up with more personalized, more meaningful treatments than the often shotgun blast that we use today. One other potential stretching a little further out is when we have robotics that are behaving more and more like humans. They have the capability to interact with each other. You're going to see that robots will become part of our daily fabric. You'll see robots participating in education, both as being taught and as educators, both in the home life, it's interacting with us, and then interacting in a care capacity. Certainly, healthcare and elder care will be a huge application for this kind of capability as it becomes more mature. So, closing thought, this notion of the singularity. So, if you're familiar with Ray Kurzweil, inventor, entrepreneur, futurist, now works with Google, he, a while back, sort of followed Moore's law to its insanely logical conclusion and said, if you just keep doing this doubling every year and a half, what happens? What does that trajectory look like? And what he did all the way back in late 1990s was plot this out over time and say, where does it go from there? And basically what it means is that by about the time that we are sitting here in the mid 2010s, we already have computers that for $1,000 can operate at the level of an insect's brain, and we're approaching a mouse's brain. By 2030, we'll have that capability for $1,000, the estimated processing speed and capacity of a single human brain. And then his date, where he calls the singularity, sort of this point of no return, is around 2050, where all of a sudden a single $1,000 chip has enough capacity to basically do all of the computation of all humans on Earth today. That's pretty heady stuff when you think about what that means. And even if he's off, there's no doubt that we will reach a point soon, and we may have already, where the future is so drastically different that we no longer have an appreciation or understanding of what that even means. What it means for us as people and our businesses is that we need to be much, much better at being flexible, at being anticipatory, to take advantage of things as they emerge, and not spend all of our planning and thought and effort on trying to sustain business as is. Because if you thought about that technology acceleration curve or adoption curve, the hidden cost behind that is the companies today that are in business were not in business 10 years ago. And that cycle time is getting even shorter. So you can't create a product that's the next big thing and then sit on that product for 50 years and have a monopoly. So it means very different organizational structures, very different R&D structures. And for us personally, it means different career structures and career trajectories, where we're thinking about things in a much more holistic and lateral or divergent fashion than we might have 50, 100 years ago. We've made it to the end. Thank you. I really appreciate you staying with us through this. Some of it could have been a little heady. Some of it might have been a little more abstract than what you might have found in your own industry, but hopefully you were able to find some nuggets, some useful pieces of information you're able to bring back into your organization. So, just to briefly recap, we talked obviously a lot about deep learning and boiling it down to its essence. I describe it as it's a large number of these stacked neural networks, meaning they sit one on top of each other. They're able to recognize more abstract, nuanced patterns. And we talked about why this has happened, and then we circled back to them when we talked about the future of deep learning. And it's these mega trends that power this capability. It's faster and cheaper hardware, it's better software, and it's obviously a lot more data, right? The big data you hear so much about in the media today. We covered a variety of ways that you can use deep learning from understanding the world around us. We talked about feature extraction. We talked about clustering and classification as ways to group things. And then we talked about prediction and recommendations, right? Two sides of the same coin there. We then got out of the cyberspace and went into the real world, started looking at human machine interaction. So things like understanding speech and handwriting recognition, being able to synthesize speech, and then taking that even one step further and looking at the machines of the world and looking at robotics and how they can move in the space around us, how they can sense what's going on around them, including sensors that we don't as humans have, and then be able to handle all of that uncertainty. And through it all, we covered way too many applications to list. Probably the most popular or the most applicable to your world are listed here. Where do we go from here? Check out other courses on O'Reilly and other internet resources, searching for things like machine learning, artificial intelligence, AI, deep learning. And I'd also encourage you to check out more on organizational change management, or OCM, because I think that's a key piece to any deep learning or really any technology application. Also encourage you to check out a few of these APIs that are becoming increasingly helpful for demonstrating capabilities very quickly. So for this rapid development, rapid prototyping. IBM Watson's a big one. Microsoft and Amazon both have machine learning now built into their platforms. Not playing favorites here. Those are just name brands you'd likely recognize, but there are many others out there. And I'd encourage you to explore around and see what's possible. Now, if you were interested in some of the really forward future thinking, sort of the end horizon of where this is all heading, I mentioned earlier Ray Kurzweil and his book, The Singularity is Near, and he's got a couple of other pieces of work. Not particularly evangelizing one set of books over another, but this is one that's an interesting read to understand more about this exponential growth in technology and where it may all head. And then another one that's interesting because it talks about the implications specifically to workforce and jobs, a book called The Lights in the Tunnel from Martin Ford. Just a few. You can go out on Amazon or other sites and search for books with those same topics that I mentioned on the last slide. You'll be well set. Follow the recommendations, the ratings and such, and you'll be well on your way. And last, just sort of mix it up a little and think about some of that divergent thinking. Throw in some science fiction. Isaac Asimov is probably the best, but there are many others. Broaden your horizon looking at what is considered science fiction now, and know that in many of like Isaac Asimov's books written, 50s, 60s, some of the technologies he envisioned millennia from now have already come to play. So it's a good way to broaden your mind.